Off the Carolina coast, a small low-pressure swirl just collided with the Gulf Stream. In hours, it could drop almost 30 millibars. That drop turns ordinary storms into monsters. Forecasters thought it would be a routine spring system. Now warnings are stretching from Virginia to Maine, and the ocean is feeding it more energy by the minute. If you find this terrifying, hit subscribe and stay with us. We will track the storm's secret engine, the lesson the last bomb cyclone left behind, and the forecast nobody wants to confirm. Brace yourselves. We begin. On Friday afternoon, a meteorologist at the Weather Prediction Center in Maryland sat down to write an outlook that should have been routine, the kind of forecast that gets read once, filed away, and forgotten by Monday. Then he looked at the latest model run. A closed upper-level low parked over eastern Canada was feeding a long trough of low pressure down into the eastern United States. The setup looked ordinary enough. Cold front sliding southeast, showers and storms ahead of it. Springtime business. But the models were starting to whisper something else, something the forecaster had to put into writing. He typed it carefully. Post-frontal rainfall would move off the east coast on Monday, followed by some potential for cyclogenesis just off the mid-Atlantic coast late next week. That word, cyclogenesis. For most people, it sounds like a science class term. For meteorologists, it is a flag. It means a storm is about to be born from nothing, out at sea, where nobody can stop it. The discussion went out at 4 in the afternoon. Within hours, the forecast offices up and down the eastern seaboard were quietly checking their guidance. Coastal cyclogenesis off the mid-Atlantic does not stay small for long. The geography alone makes sure of that. Cold air pushing down from Canada, warm water pushing up from the south. They meet right where the coastline curves outward into the ocean, right where ships sail, right where 80 million Americans live. The first model runs showed a developing low. The second showed it deepening faster. The third made forecasters lean forward in their chairs. By Saturday morning, the language in the public discussion started to shift. Not panicked. Not yet. Just careful. The kind of careful that experienced forecasters use when they know something the public does not. A wavy cold front, multiple shortwave energies, locally heavy rainfall up the Carolina coast. Translation: a storm was forming, and it was forming in the worst possible spot. Here is what most people do not realize. The eastern coast of the United States is one of the most explosive storm factories on the planet. Year after year, decade after decade, the same patch of ocean produces some of the most rapidly intensifying weather systems anywhere. Storms that double in strength overnight. Storms that bend the rules of how fast pressure can drop. And the reason is sitting right offshore. A river of warm water, moving north, pumping heat into the air, waiting for the right cold front to ignite it. The forecaster knew all of this. So did the offices in Norfolk, in Mount Holly in Boston. They had seen it before. January 2018. The Grayson storm. A pressure drop so violent it set records. This time the calendar said May. Spring. Nobody expects monsters in spring, but the satellite loop on Friday night was already starting to show a swirl, a small one, loose, disorganized, the kind of feature most viewers would scroll right past on a weather map. The forecasters did not scroll past. They zoomed in. They ran the numbers again. They compared it to the analog cases. They looked at the sea surface temperature charts. Then they wrote one more line into the outlook for the following week. And what they wrote next is where the real warning began. The first computer model to look at this storm gave a polite, almost boring answer. A weak low, a little rain, some breezy conditions on the coast. Move along. That model was wrong. Computer models are extraordinary tools. They take billions of measurements from satellites, weather balloons, ocean buoys, and ground stations, then crunch the entire global atmosphere into a forecast. They are right far more often than they are wrong. But they have a stubborn weakness. They struggle with rapid intensification. When a storm deepens slowly, models do beautifully. When a storm explodes, models often miss, sometimes by 10 millibars, sometimes by 20. And in this corner of the Atlantic, 20 millibars is the difference between a windy weekend and a regional disaster. The reason has to do with how models see the ocean. Most operational models treat the sea surface as a smooth blanket. Warm here, cool there, with average temperatures over wide areas. The real ocean is nothing like that. It has fronts, eddies, swirling rivers of heat and cold tangled together like marble cake. Right off the east coast, that marble cake is at its most chaotic. The Gulf Stream pushes north along the continental shelf, breaking off warm rings that drift into colder water. Each warm ring is like a hidden battery. A storm that crosses one can suddenly find itself sitting on a furnace. Models often miss those batteries, so they underestimate the fuel, so they underestimate the storm. There is a second blind spot. The atmosphere above. When a jet streak races overhead at high altitude, it sucks air up out of the storm below, like a chimney. That suction lowers surface pressure even faster. Predicting where that jet streak will sit and how strongly it will pull requires almost perfect timing. A few hours off in the model, 100 miles off in position, and the entire forecast collapses. By Saturday morning, 3 different forecast models were starting to disagree with each other. The American GFS pushed the storm farther offshore. The European model held it closer to the coast. The Canadian model deepened it harder than either. When models disagree like that, forecasters lean on something called ensembles. Instead of one forecast, the computer runs dozens, each with slightly different starting conditions. The spread of those runs tells you how confident the forecast really is. The ensemble spread for this storm was wide, not catastrophic wide, but wide enough that the highest end members were showing pressure values that experienced forecasters whispered about in private. Here is the uncomfortable truth. Models often run cold on storms like this until the very last moment. Then, 24 hours before impact, they suddenly snap into agreement. The storm gets 10 or 15 millibars deeper than the original forecast. Warnings get upgraded in a hurry. Communities scramble. It happened in 2018. It happened in 2022. It has happened so many times along this coast that meteorologists have a quiet name for it: the model surprise. Right now, the model surprise window is closing. The storm is starting to organize on satellite. The pressure trace at coastal buoys is beginning to fall faster than the original outlook suggested. Forecasters are watching, updating, calling their counterparts in neighboring offices, because the next 24 hours are when the truth comes out. And the truth is starting to look worse than the maps from Friday. But the real reason this storm is overperforming is not in the air at all. It is in the water beneath it. And what that water is doing right now would shock most people who live on the coast. If you could shut off the Gulf Stream tomorrow, the East Coast would probably never see a bomb cyclone again. That is how important it is. The Gulf Stream is a river inside the ocean. It starts near the tip of Florida, runs north along the coast, then peels off near Cape Hatteras, and crosses the Atlantic toward Europe. At its strongest, it carries more water than every river on Earth combined, and it is warm, tropical warm. Even in the dead of winter, the surface of that current can sit in the 70s. When cold air from Canada slides off the continent and meets that warm current, the atmosphere goes a little crazy. Think of it this way: warm water gives up heat to the cold air above it. That heat makes the air rise. Rising air leaves a hole at the surface. Surrounding air rushes in to fill the hole, and the rotation of the planet bends that rushing air into a spin. A spin is a low-pressure system. A faster spin is a storm. A storm sitting directly above the Gulf Stream is something else entirely. The current does not just warm the air, it also pumps moisture upward at staggering rates. As warm, moist air from tropical regions rises, it meets cold Arctic air, creating instability. The clash of these air masses causes a low-pressure area to intensify. When that moisture condenses into clouds high up in the storm, it releases something called latent heat. It is the energy locked inside water vapor, and when the vapor turns back into droplets, all that hidden energy gets dumped straight into the storm. It is like throwing gasoline on a campfire. The storm uses that heat to push higher into the atmosphere, and the deeper a storm reaches into the upper sky, the lower its surface pressure falls. Lower surface pressure means stronger winds. Stronger winds means bigger waves. Bigger waves means more ocean spray, which means more moisture, which means more latent heat. The cycle keeps feeding itself. Meteorologists have a term for this. They call it the warm sector engine. And the Gulf Stream off the Carolinas is the most powerful warm sector engine on the planet between October and May. Now consider the storm forming offshore right now. Forecast tracks have it crossing directly over a particularly warm slug of Gulf Stream water just east of the Outer Banks. Sea surface temperatures there are running a few degrees above normal for early May. A few degrees does not sound like much. It is enormous. Every 1 degree increase in sea surface temperature can boost a storm's available energy by several percent. Across a wide swath of ocean, that adds up to staggering amounts of fuel. This is why meteorologists keep their eyes glued to ocean charts during storm setups. The atmosphere can be ready, the cold front can be perfect, the jet stream can be aligned, but without that warm water underneath, the storm fizzles into nothing. With the warm water, it detonates. Right now, the satellite is showing the first signs of that detonation, a loose swirl tightening, convective bursts firing on the eastern side, the cloud tops getting taller, the pressure beginning to fall. The furnace is lit, and the next ingredient just arrived from the north. Cold fronts are usually clean lines on a weather map, a sharp blue boundary, one side warm, the other cold. They move in straight lines and do their work in a few hours. The front feeding this storm is doing none of that. It is wavy. Forecasters love that word. Wavy is code for trouble. A wavy cold front means the boundary is bending, buckling, looping back on itself. Each bend is a place where new low pressure can form. Each loop is a place where the atmosphere can suddenly twist into something bigger. This particular front started its journey in northern Canada earlier in the week. Cold, dry air pouring south behind it. By Saturday, it had reached the Great Lakes. By Sunday, it was sweeping into the mid-Atlantic. Showers ahead, clear skies behind. Normal so far. Then the front hit the warm air sitting off the Carolina coast. A flat front would have just kept moving east, off the coast, out to sea, but the upper level pattern was holding the front back over land while letting its southern end push offshore. The front bent. The bend got tighter. The tightest part of the bend started to spin. That is where the new storm was born. Meteorologists call this process secondary cyclogenesis. The original front becomes the parent. A new low-pressure system, the child, forms along the kink. Sometimes the child stays small. Sometimes the child grows so fast that within a day it is bigger and stronger than its parent. The signs that this child storm is going to be the dangerous kind are already showing up. First, the front is not weakening as it moves over the warm water. It is intensifying. The temperature contrast across the boundary is sharpening, not blurring. Cold air on one side, tropical air on the other. The clash is sharpening like a knife being honed. Second, the upper level support is excellent. A jet streak, a fast-moving river of high-altitude wind, is positioning itself perfectly above the surface low. That overhead suction is going to pull air up out of the storm and let surface pressure plummet. Third, the moisture supply is endless. The Gulf of Mexico is open. The Atlantic is open. Both are pumping warm, humid air into the system at the same time. Forecasters look at all three of those ingredients together and call it the textbook setup. When you see all three, You do not ask if a bomb cyclone is going to form. You ask how deep it is going to go. The wavy front matters in another way. It controls where the worst weather lands. Storms that form along clean fronts move in predictable paths. Storms that form on wavy fronts can stall, jog, or curve in unexpected directions. Communities that thought they were safe can suddenly find the storm parking right over them. Cities that were forecast to take a direct hit can find themselves on the dry side. That uncertainty is what makes coastal forecasters nervous. The current model spread for this storm shows possible tracks ranging from just off the Delmarva Peninsula to almost over Boston Harbor, 100 miles east, and the worst winds stay offshore, 100 miles west, and the same winds tear apart roofs from Long Island to Cape Cod. The wavy front is going to decide which version actually happens, and that front is wobbling more, not less, by the hour. Every meteorologist remembers the first time they saw a real bomb cyclone happen on radar. The pressure plot is what does it. A line on a graph that should slope gently, a line that suddenly tips downward like the side of a cliff. 48 hours of patience, then 6 hours of panic. The official threshold is precise. A bomb cyclone is set apart by its rapid rate of intensification, which corresponds to a decrease in atmospheric pressure of 24 millibars or more per day at 60 degrees latitude, and a decrease of about 17.8 millibars or more per day at 40 degrees latitude. The math sounds dry, the reality is anything but. 24 millibars in 24 hours. Most storms in your lifetime have not done that. The ones that have are the ones you remember by name, the ones that closed airports for days, the ones that left whole counties without power for a week, the ones that pulled the Atlantic up and over the dunes and into living rooms. Why is that exact number so important? It comes from research done in the late 1970s. Scientists studied thousands of storms across the North Atlantic and noticed that something dramatic happened to a small fraction of them. Their pressure plots did not just go down, they collapsed. The storms intensified so quickly that surrounding weather patterns could not keep up. By the time forecasters realized what was happening, the storm was already at peak strength. The researchers needed a way to flag these monsters early. They picked 24 millibars in 24 hours as the cutoff. Anything that dropped that fast was no longer a normal extratropical storm. It was something else, a bomb. The metaphor stuck. So did the science. Today, forecasters watch pressure tracers during storm setups, the way doctors watch heart monitors. A few millibars drop per hour is healthy. 6 millibars per hour is concerning. 10 millibars per hour is the bomb threshold turning red. The current storm offshore is not yet at that pace. Right now, its central pressure is dropping at maybe 4 or 5 millibars in 3 hours. Steady, organized, deepening. But the 18-hour window where things get dangerous is just opening. If the upper level support strengthens as forecast, the rate of pressure drop will accelerate. Models are now hinting at a possible 30 to 35 millibar fall in 24 hours during the peak intensification phase. That would put this storm well above the bomb cyclone threshold and into the category of historically significant systems. Here is the part forecasters do not love saying out loud. The faster a storm bombs, the worse the impacts tend to be. It is not just about how strong the winds get, it is about how fast they get there. A normal storm gives coastal communities maybe 48 hours of warning. People board windows, move boats, top off generators, stock food, evacuate barrier islands. A bomb cyclone gives them less, sometimes much less. The pressure drops so fast that watch becomes warning becomes emergency in a single news cycle. People who were told the day before that the storm would be manageable wake up to find the worst is hours away, not days. That speed is the killer. The 24 millibar rule was not invented to scare anyone. It was invented to give forecasters a number that would make them call in extra staff, alert emergency managers, and break the normal chain of caution. Right now, that number is starting to flash. Quietly, in private discussions, between offices, the public will hear about it soon enough. If a storm wants to explode, there is one stretch of ocean it should head for, the waters between Cape Hatteras and Cape Cod. Meteorologists have known this for decades. In the northern hemisphere, the maximum frequency of explosively deepening cyclones is found within or to the north of the Atlantic Gulf Stream, the Kuroshio Current in the western Pacific, and in the eastern Pacific. That is a polite way of saying the East Coast is one of two places on the planet where storms most often go nuclear. The other is off the coast of Japan. Everywhere else, bomb cyclones happen sometimes. Here, they happen reliably. The reason is geography. Brutal, unfair, beautiful geography. The continent ends at the east coast. Cold air spilling off the land hits warm water immediately. There is no slow transition zone. There is a hard line. A few miles offshore, the temperature can jump 20 degrees. That kind of contrast is rocket fuel for storm formation. Stack a few more ingredients on top, and the area becomes an explosive cyclone factory. The Appalachian Mountains funnel cold air down the eastern side of the continent in tight ribbons. The jet stream parks itself overhead more often here than almost anywhere else in North America. The continental shelf drops sharply, allowing the Gulf Stream to run close to land. Each one of these features alone would create some interesting weather. Together, they create the worst real estate on the map for storm avoidance. There is more. There are three types of winter and spring coastal storms: Miller Type A, Miller Type B, and the Bahamas Low. Each type has its own personality. Miller Type A storms come up from the Gulf of Mexico. They cross northern Florida, then ride up the coast, gaining strength every mile. They are the most common, and they tend to hit the entire seaboard. Miller Type B storms form inland over the Midwest. They march east, weaken as they cross the Appalachians, and then a brand new storm pops up offshore. The new offshore storm often becomes far stronger than the original inland system. These are the trickiest to forecast, because the handoff happens in just a few hours. The Bahamas Low forms farther south, off the southeast Atlantic coast. It is rarer but capable of producing some of the most intense systems on record. The storm forming right now is showing characteristics of a Type B handoff. The inland trough is feeding the new offshore low. The original system is fading. The child is taking over. Type B handoffs have a long history of catching people off guard. A weakening inland storm makes news look manageable. Then the new offshore low explodes, and suddenly the worst weather is hitting cities that were never directly under the original threat. Add another factor. The North Atlantic Oscillation is currently in a phase that allows cold air to push deep into the eastern United States. This sharpens the temperature contrast at the coast. The sharper the contrast, the faster a storm can intensify. Then add the Bermuda High. Its position controls whether storms get steered out to sea or pushed back toward land. Right now, it is sitting in a configuration that nudges storms northeast along the coast, keeping them just close enough to drag heavy rain, wind, and surge inland for days. Pull all of these threads together and you get a picture of why the people who study this stuff do not sleep well during setups like the current one. The geography is wrong, the currents are wrong, the cold air is in the wrong place, the high pressure is in the wrong configuration, the temperature contrasts are too sharp, or, depending on how you look at it, every single ingredient is exactly right for a storm to do its worst work. The factory is open. Down at sea level, the storm pulls air in. Up at altitude, something else has to be pulling air out, otherwise the whole system stalls. That something is the jet stream. Most people think of the jet stream as a wind that blows airplanes faster. That is true, but it is the smallest part of what it does. The real magic of the jet stream is that it acts like a chimney for storms. Without it, even the warmest ocean and the sharpest cold front would only produce a mediocre system. A jet streak is a faster section of the jet stream, a localized burst of speed where the wind is blowing maybe 200 miles per hour at 35,000 feet. As that streak races along, the air ahead of it spreads outward, and the air behind it converges. The spreading part is the key. When air spreads out at high altitude, it leaves a vacuum. To fill that vacuum, air from below has to rise. Now imagine a developing storm sitting directly underneath the spreading region of a jet streak. The storm is already trying to make air rise on its own. The jet streak comes along and adds extra suction from above. Surface pressure plummets. The storm deepens. That is the chimney effect. Forecasters look at jet streak position the way carpenters look at a level. If the alignment is off by even 100 miles, the suction can land in the wrong spot. The storm gets disorganized, energy gets wasted, the intensification stalls. When the alignment is perfect, the storm becomes a tower, a column of rapidly rising air that stretches from the ocean surface all the way to the bottom of the stratosphere. 35,000 feet of organized chaos. The current setup off the east coast is showing exactly that kind of perfect alignment. A jet streak is dropping down from southern Canada, accelerating across the Great Lakes, and heading directly for the developing storm. By Sunday night, the streak is forecast to position its left exit region right over the surface low. The left exit region is the most favored spot for upward motion. It is where the chimney sucks hardest. When that happens, the storm typically responds within hours. Pressure falls accelerate, cloud tops shoot upward, convection fires near the center. Satellite images start showing the classic comma shape that experienced forecasters recognize from 1,000 previous storms. There is another complication. The jet streak itself is being fed by a powerful temperature gradient between Arctic air over Canada and tropical air over the Atlantic. That gradient is unusually strong for May. Stronger gradients mean stronger streaks. Stronger streaks mean stronger suction. Some models are now showing the streak reaching speeds that would be more typical of February than late spring. That out-of-season strength is one of the reasons the storm is overperforming its original forecast. Here is what makes the chimney metaphor especially useful. A real chimney can fail in two ways. It can be blocked at the top, in which case smoke backs up, or it can be pulled too hard from above, in which case the fire roars out of control. Storms work the same way. Too little upper-level suction, and the system suffocates. Too much, and the system runs away. The current setup is heading toward the second case. Too much suction. A storm being pulled deeper than the surrounding atmosphere can naturally support. That kind of imbalance is exactly what creates record-breaking pressure drops. The chimney is roaring, the fire is feeding. The roof of the storm is shooting up toward the stratosphere, and the pressure at sea level is starting to drop in a way that has experienced forecasters quietly cancelling weekend plans. The general public does not see it, the forecasters do. 3 days before a major storm, there is almost always a moment when the data starts whispering, not shouting, just whispering. A few model runs trending stronger, a satellite image looking a little too organized, a buoy reading a little too low. Those whispers are when the real work starts. For this storm, the whispers began on Wednesday. A long-range model run came in showing a deepening offshore low for the following Sunday. The forecaster on duty noted it, but did not alarm anyone. Long-range models often invent storms that never happen. By Thursday, the same model showed it again. Slightly different position, same depth. Then the European model agreed. That is when the second alarm went off in the back of forecasters' minds. When two different models from two different countries running on two different sets of equations both produce the same storm in the same place, it stops being an invention. It starts being a forecast. Phone calls began between regional offices. Norfolk talked to Wakefield. Wakefield talked to Boston. The kind of conversations that do not make the news, but quietly set the entire eastern seaboard's forecast operations into motion. Marine forecasters were the first to issue formal language. The NWS Ocean Prediction Center placed the low over the western Atlantic, off the US east coast, and was forecast to deepen as it moved farther into the North Atlantic. That is the polite way of saying mariners need to start running for harbour. Notice the language. Forecast to deepen, not might deepen, not could deepen. That is high confidence text from an agency that does not use it lightly. The Weather Prediction Center followed up with a separate discussion outlining the broader pattern. Coastal cyclogenesis. Locally heavy rainfall up the Carolina coast, showers and thunderstorms across the mid-Atlantic and northeast. Each phrase carried weight. To a meteorologist, those are not just words. They are flags. They mean a system has been identified, the formation zone has been mapped, and the impact areas have been narrowed down. Behind the scenes, hurricane and ocean specialists were also tuning in. Even though this is not a tropical system, the techniques used to monitor it are nearly identical. Satellite pressure estimation, microwave imagery to peek inside the cloud shield, surface buoy data to track how fast pressure was actually dropping in real time. By Friday evening, a quiet handoff had happened. The storm was no longer a model possibility. It was a real low, visible on satellite, with a measurable pressure moving at 30 miles per hour. That is the moment when forecasting transitions from prediction to observation. The public did not feel any of this. The cable news weather hits were still showing pleasant spring weekends. The smartphone apps were still running on the original model output, which underestimated the system. The first social media posts about the storm were getting maybe a few hundred shares. Inside the forecast offices, things were different. Senior forecasters were being called in. Briefings were being prepared for state emergency managers. Coastal communities were being put on internal watch lists. The whispers had become a steady hum. By Saturday morning, the National Weather Service had begun to draft impact statements. Wind, rain, surge, beach erosion, power outages. The list was getting longer with every model cycle. Then came the first headline, not on the front page. Tucked away in the weather section, a small, careful article noting that a storm could affect parts of the coast in the coming days. The article did not say bomb. It did not say emergency. It did not need to. The forecasters reading it knew what was coming. The hum was about to turn into a roar. To understand why this storm is going to be so much worse than a typical spring system, you have to understand what happens when very cold air meets very warm water. Cold air is dense, it sinks, it hugs the ground. Warm water is generous. It gives off heat in every direction. It evaporates moisture upward without stopping. When cold air slides over warm water, the bottom layer of air heats up almost instantly. The newly warmed air becomes lighter than the cold air still pouring in above it. So the warmed layer rises, the cold air sinks behind it. The cycle repeats, faster and faster, until the entire boundary between the two becomes a wall of rising motion. That wall of rising motion is where storms grow. The strength of the wall depends on one thing: the temperature contrast. 2 degrees of contrast produces nothing. 10 degrees produces breezy weather. 20 degrees produces a real storm. 30 degrees produces a beast. The current system has 30. Behind the cold front pushing offshore right now is air that originated in northern Canada earlier this week. It is unusually cold for May. Forecasters expected it to moderate as it moved south, and it did, but not enough. Ahead of the front, sitting over the Gulf Stream, is air that has been baking over warm tropical water for days. Surface dew points are in the upper 60s and lower 70s. That is summer humidity in early May. When the cold front hits the warm sector, the contrast is enormous. Surface temperatures drop 15 to 20 degrees in a single hour as the front sweeps through. That is the kind of temperature change normally associated with strong winter cold fronts, not spring ones. The atmosphere reacts violently to that kind of contrast. Air that hot and humid wants to rise, Air that cold and dense wants to sink. Both happen simultaneously. The result is intense thunderstorms along the front itself, plus rapid spin-up of low pressure where the boundary kinks. There is another factor that makes this contrast particularly dangerous. Warm air can hold a lot more moisture than cold air. Every degree of warming roughly doubles the amount of water vapor the air can carry. The warm sector air feeding this storm is loaded with moisture that the cold air simply cannot retain. When the warm air rises and cools, all that moisture has to go somewhere. It condenses into rain. Heavy rain, sometimes catastrophic rain. The forecast rainfall totals from this storm are starting to creep upward. Initial estimates of 1 to 2 inches over coastal areas have already been revised. Some models are now showing isolated totals approaching 6 or even 8 inches in spots where rainbands stall over the same towns for hours. 8 inches of rain in a single storm is enough to flood streets, overwhelm storm drains and inundate low-lying neighborhoods. It is also enough to trigger landslides in the higher terrain inland. The temperature contrast also drives the wind. The bigger the difference between warm and cold air masses, the stronger the pressure gradient between them. The stronger the gradient, the harder the wind blows. Initial wind forecasts called for gusts of 40 to 50 miles per hour at the coast. Those numbers are now being adjusted upward. Some inland locations are being warned about gusts approaching 70. Coastal locations could see gusts in excess of 80. 80 miles per hour is hurricane force. The contrast that is fueling all of this is going to peak Sunday night into Monday morning. That window is when the storm is expected to deepen most rapidly, the winds will be at their worst, and the rain will be coming down hardest. The clash is coming, and the energy released by that clash is going to be remembered. If you took a thermometer to the surface of the Atlantic right now, somewhere off the Outer Banks, the reading would surprise you. It would be in the 70s, possibly the upper 70s, in some warm core eddies. For early May, that is hot. Sea surface temperatures take longer to change than air temperatures. The ocean has thermal inertia. It absorbs heat slowly during summer and releases it slowly during winter. By early May, the surface should still be cool from the winter cooling cycle, with temperatures gradually rising as the sun strengthens. The current readings are not acting like that. They are running well above average for the date, in some patches 4 or 5 degrees above the long-term mean. 4 or 5 degrees does not sound like much when you are thinking about a hot tub or a swimming pool. In an entire ocean basin, it is a colossal amount of stored energy. A few degrees of extra warmth across a wide region of ocean represents enough heat to power thousands of strong storms. That heat does not go away. It either evaporates into the atmosphere as water vapor or stays in the upper ocean waiting for a storm to come along and tap it. The storm currently forming offshore is going to tap a lot of it. Why is the ocean so warm right now? The answer is layered. Part of it is natural variability. Sea surface temperatures fluctuate from year to year based on wind patterns, ocean currents, and the position of large-scale features like the Bermuda High and the North Atlantic Oscillation. Some years run cool, some run warm. Part of it is the long-term warming trend that has been documented across every major ocean basin over the past several decades. The global ocean is roughly 2.5 degrees Fahrenheit warmer at the surface than it was in pre-industrial times, on average. The North Atlantic has warmed even more in some regions. Part of it is the recent state of the Atlantic itself. Waters across the Atlantic are expected to be warm throughout 2026, though not as high as in 2023. Even at slightly lower than the recent record warmth, the Atlantic remains anomalously hot for the time of year. The implications for the current storm are significant. Warm water means more evaporation. More evaporation means more moisture for the storm to convert into rain and latent heat. Latent heat is the most efficient fuel a low-pressure system can find. There is also the effect on storm track. Warm water tends to attract storms. Low-pressure systems naturally drift toward warm sea surface temperature anomalies because the warm water enhances the rising motion at the storm's center. The Atlantic right now has a tongue of unusually warm water extending up the east coast, almost like a glowing path that says, "Come this way." The storm is following it. There is one more layer to consider. The 2026 hurricane season is just weeks away. Forecasters are also keeping a close eye on the weeks before and just after the official start of the Atlantic hurricane season on June 1. With warm waters firmly in place in the areas where storms typically develop early in the season, it may not take much to have tropical activity fire up around the same time that the season officially gets underway. That is a polite way of saying the warm water does not stop being a problem after this current storm passes. It stays, it builds, it waits. Every storm that crosses warm water steals a little of its heat, but most of the heat stays. By the time June arrives, the Atlantic could be primed for early tropical development. For now, though, all of that energy is concentrated in one developing low-pressure system off the Carolina coast, and that system is about to do exactly what overheated water lets storms do. It is about to grow up faster than anyone expected. The map of expected wind impacts from this storm is starting to look ugly. Coastal forecasters have a saying, "The storm gets the headlines. The wind does the damage." Headlines focus on rainfall totals, snow accumulations, coastal surge. Wind is harder to photograph, harder to film, harder to convey. But of all the elements a strong storm produces, wind is usually what does the most physical and economic harm. The current forecast has gusts reaching 70 miles per hour or higher across a wide swath of the eastern seaboard. Some isolated spots could see 80. Mountain peaks in the Berkshires and the Catskills could see 90 or more. 80 miles per hour is not a coastal problem. 80 miles per hour is a regional problem. At 40 miles per hour, the wind is annoying. Loose objects fly. Trash cans tumble. Tree branches snap. At 60 miles per hour, things change. Power lines start to come down. Shingles peel off roofs. Older trees, especially ones with shallow root systems or recent waterlogging, begin to topple. Highway signs strain against their bolts. At 80 miles per hour, it gets serious. Healthy trees fall. Power outages spread across entire counties. Roof damage becomes widespread. Mobile homes can be tipped over. Vehicles on bridges and overpasses get pushed into other lanes. What makes this storm particularly dangerous from a wind standpoint is two things. First, the duration. Bomb cyclones do not blow hard for an hour and quit. They blow hard for half a day or longer. Sustained wind over many hours does cumulative damage in a way that brief gusts do not. A tree that survives one 80-mile-per-hour gust may not survive the 100th 80-mile-per-hour gust 6 hours later. Second, the saturated ground. The same storm bringing the wind is also bringing heavy rain. Soil that is already soaked offers little resistance to root systems trying to hold trees upright. The combination of saturated ground and sustained wind is what brings down even healthy mature trees. When healthy trees fall, they take power lines with them. They block roads. They crush vehicles and roofs. There is also the issue of flying debris. At hurricane-force wind speeds, anything not tied down becomes a missile. Patio furniture, trash cans, construction materials, roofing shingles. A piece of plywood traveling at 70 miles per hour can punch through a window like a battering ram. The areas of greatest concern for severe wind are not always at the immediate coast. The strongest wind in a coastal storm often shows up just inland, where the gradient between the storm center and the surrounding high pressure tightens. For this storm, that means cities like Hartford, Springfield, and parts of southern New Hampshire could see wind impacts as severe as anything along the immediate shoreline. Power utilities across the region have already been making preparations. Crews from neighboring states have been pre-positioned, repair vehicles are staged, mutual aid agreements have been activated. History suggests it will not be enough. Major bomb cyclones routinely knock out power to millions of people for days. Some neighborhoods stay dark for a week or longer. The hardest hit areas can take 2 weeks to fully restore. The wind threat does not end at the coast. It does not end after one bad hour. It rolls in like a tide, and once it is up, it stays. Storm surge is the quiet killer of coastal storms. Wind makes the news. Surge makes the funeral notices. Across the worst storms in American history, the single biggest cause of death has not been collapsing buildings or flying debris. It has been water rising up out of the ocean and pushing inland faster than anyone could outrun it. The current storm forming offshore is not a hurricane. The surge will not be in the same league as Katrina or Sandy, but it does not have to be. The shoreline of the eastern seaboard is vulnerable in ways that even moderate surges can exploit. Surge happens when a storm's wind pushes ocean water toward shore faster than the water can drain back out. The longer the wind blows in the same direction, the higher the water piles up. Combined with the storm's low pressure, which lets the ocean surface bulge slightly upward, the result is a temporary rise in sea level that can flood neighborhoods miles from the actual coast. For this storm, the surge threat is highest along the mid-Atlantic and southern New England coast. Forecasters are watching tide cycles carefully. If the peak surge hits at high tide, the water can climb several feet higher than it would at low tide. The coincidence of timing matters as much as the storm's strength. The geography of the East Coast does not help. Long Island Sound, Narragansett Bay, the Chesapeake. Each of these embayments acts as a funnel. Water pushed in by storm wind cannot easily escape. It piles up against the back end of the bay, raising water levels far above the open coast. Areas like the upper Chesapeake near Annapolis, the eastern shore of Virginia, and the south shore of Long Island are particularly exposed. There is also the issue of beach erosion. Even when the storm surge does not reach inland buildings, it can chew away at dunes and beaches at staggering rates. Hurricane Erin is a prime example of a high-impact storm that didn't make landfall. In August 2025, pounding waves and storm surge from the hurricane caused severe beach erosion along the Atlantic seaboard. By the end of the season, multiple houses had collapsed into the ocean, following Erin and other coastal storms. That precedent is sitting heavy on the minds of coastal officials right now. A storm that never makes landfall can still take homes off cliffs. A storm that stays offshore can still strip a beach down to its underlying clay layer. A storm that looks unimpressive on the surface map can still destroy hundreds of millions of dollars worth of coastal infrastructure if its winds keep pushing water at the same shoreline for a day and a half. The Outer Banks are especially vulnerable. The barrier islands there have been losing real estate to the Atlantic for decades. Each major storm accelerates the process. Each storm chews away another foot of dune. Eventually, the foundations beneath beachfront homes become exposed. When that happens, a moderate storm becomes the final straw. The current storm's surge is forecast to peak at 3 to 5 feet above normally dry land along the worst affected stretches. That sounds modest compared to hurricane surges. It is not. 3 feet of moving saltwater is enough to lift a car off a road and float it into a building. 5 feet is enough to fill the first floor of a house. Even a foot of water moving at storm speeds is enough to knock an adult off their feet. Coastal evacuation orders have started going out for the most exposed barrier island communities. Bridges are being prepared for closure. Emergency management teams are pre-staging equipment. The water is coming. The only question now is how high it climbs and how far inland it reaches before the storm finally weakens and the wind shifts. There is something uniquely heartbreaking about watching a house fall into the ocean. It does not happen the way movies show it. The structure does not slide gracefully into the surf with a final splash. It falls in pieces. A deck collapses first, then a corner of the foundation, then the entire seaward wall. The roof tilts, windows shatter, furniture spills out. In the worst cases, it happens during a single tide cycle, 6 hours from intact home to floating debris. Coastal North Carolina has been losing houses this way for years. Each major storm takes another handful. Between storms, the beach crews truck in sand to rebuild dunes. The next storm sweeps the new sand back out to sea. The cycle continues. The current storm is going to accelerate that cycle. What makes coastal erosion during a storm so severe is the combination of factors hitting the beach simultaneously. Wind drives waves into the sand. The waves pick up the sand and pull it offshore. The storm surge raises the water level, so the waves attack higher sections of the beach. The duration of the storm gives the waves enough time to do real damage. When all four factors line up, beach erosion can happen at jaw-dropping rates. 5 to 10 feet of beach width can vanish in a single storm, in some cases more. The geometry matters. A beach with a wide, gently sloping sandy front absorbs wave energy across a broad area. A beach with a narrow, steep front has nowhere to dissipate the energy, except by losing material. Most East Coast beaches are somewhere in between, but the recent trend has been toward narrower, steeper profiles as previous storms have already done their work. For the most vulnerable communities, the question is no longer whether erosion will happen. It is whether enough beach is left to lose. Outer Banks villages like Rodanthe have become almost famous for the wrong reason. Dramatic videos of houses collapsing during routine high tides have made the rounds online. Property owners have moved entire structures back from the beach, sometimes more than once. Some houses sit on stilts that look impossibly tall, designed to keep the building above water that was never supposed to reach that high. This storm is going to test all of those preparations. There is also the issue of dune destruction. Dunes are the first line of defense for inland communities. They absorb wave energy, block surge, and slow saltwater intrusion. When dunes get flattened, the inland areas behind them become exposed to direct wave action. Building dunes back up is slow work. It takes years for natural processes to rebuild a healthy dune system. Engineered dune restoration can speed things up, but costs millions per mile. The communities about to lose their dunes do not have those millions. They have whatever the federal disaster declaration eventually provides, weeks or months down the road. There is one more piece to the erosion story that does not get talked about enough. The sand has to go somewhere. When a storm pulls sand off the beach, it does not vanish. Some of it gets deposited in offshore sandbars where it can eventually wash back ashore over the following months. Some of it gets carried by longshore currents to neighboring beaches, where it builds up. Some of it is lost permanently into deeper water, where it never returns. Communities downstream of major erosion events sometimes benefit. Communities at the source lose forever. The current storm's wave field is going to be enormous. Combined with the duration of the wind, it will cause serious erosion from Virginia north into New England. Some communities will lose multiple feet of beach. A few will lose structures. The pictures will go viral by Tuesday morning. The lessons, as always, will be ignored by Tuesday afternoon. A storm that is moving fast does limited rain damage. A storm that stalls is a different animal. The current system has the potential to slow down dramatically as it interacts with the upper-level low parked over eastern Canada. If that happens, certain areas could end up underneath rainbands for many hours longer than the original forecast suggested. That kind of stalling produces flash flooding. Flash flooding is the most underestimated weather threat in the United States. It kills more people in an average year than tornadoes, hurricanes, and lightning combined. Most of the deaths happen in vehicles. People drive into water that looks shallower than it is. The car gets caught in the current carries it downstream into deeper water. When a storm stalls over a saturated landscape, urban areas become especially vulnerable. Storm drains designed to handle 2 inches of rain in an hour cannot keep up with 4 inches in an hour. Streets fill with water. Underpasses become death traps. Basements flood. The forecast precipitation for this storm is being revised upward as the system organizes. Some areas are now being warned about totals exceeding 6 inches over a 36-hour period. A few isolated locations could see 8 or more if rainbands park overhead. Rainbands are tricky things. They are arms of intense precipitation that wrap around the central low pressure. They rotate with the storm, but can also stall in place if the broader steering currents weaken. When a rainband stalls, the ground beneath it gets pummeled with rainfall rates of 2 or 3 inches per hour for hours at a time. That is enough to overwhelm almost any drainage system. The Appalachian foothills are particularly vulnerable to this kind of flooding. Steep terrain combined with already wet soil from earlier spring rain means that anything falling out of the sky runs off almost immediately. Streams rise within minutes, rivers crest within hours. Communities in the Upper Susquehanna, Upper Hudson, and Connecticut River valleys are watching forecasts nervously. So are towns along the Delaware. Each of these systems has flood histories going back centuries. Each has paid the price for stalled rain events before. Urban flooding is a separate issue. Cities like Philadelphia, New York, and Boston have aging stormwater systems that can be overwhelmed by even moderately intense rainfall. Flash flooding during major storms has become almost routine in certain neighborhoods. The combination of storm surge from the coast and freshwater flooding from inland creates what hydrologists call compound flooding. The river cannot drain because the ocean is too high. The ocean cannot drain because the wind is still pushing water inland. The whole system locks up. Water levels in low-lying areas rise from both directions simultaneously. For coastal cities like New York, compound flooding events have become a recognized threat. Subway stations have been refitted with flood barriers. Critical infrastructure has been raised above expected flood levels. Pumping systems have been upgraded. Whether all of those upgrades will be enough for this storm depends on factors that are still being calculated. Rainfall maps are being redrawn every few hours. The areas of greatest concern are shifting as the storm's projected track adjusts. Coastal South Carolina and North Carolina could see the heaviest rain. Southeastern Virginia is in the high-risk zone. The Delaware Bay region, the New York metropolitan area, eastern Massachusetts. Each of those zones has its own hydrology. Each will react differently to the same amount of rain. What they share is vulnerability. Each is heavily urbanized. Each has populations measured in millions. Each has infrastructure that was built for a smaller, slower, drier century. The rain is coming. In some places, it will simply pass through. In others, it will linger long enough to do real damage. Which places end up in which category will depend on small adjustments in the storm's forward motion that nobody can predict precisely yet. Power grids are quiet things. You barely think about them until they fail. When a major storm hits the eastern seaboard, the grid is the second casualty after the trees, often within the same minute. A tree falls on a power line, the line snaps, the circuit trips, and a neighborhood goes dark. Multiply that by 10,000. That is what a bomb cyclone does to a regional power grid. The current storm has the potential to knock out service to several million customers across the affected states. Utility companies are bracing for it. Crews from as far away as the Midwest have been requested. Mutual aid agreements with utilities in unaffected regions have been activated. Repair vehicles are being staged at strategic locations along the projected impact zone. History gives a good sense of what to expect. By Monday, January 26th, snow covered more than half of the contiguous United States, and extreme cold warnings with dangerously cold temperatures were expected to persist for days. About 800,000 customers remained without power, with the most significant electrical impacts seen in Tennessee, Mississippi, and Louisiana. That was a winter storm earlier this year. The 800,000 customer figure was considered relatively manageable by industry standards. A bomb cyclone of the kind currently developing could push outage numbers 2 or 3 times higher. The most exposed parts of the grid are the older overhead distribution lines that snake through tree-heavy neighborhoods. Modern infrastructure in newer developments tends to be buried, which protects it from wind and tree damage. Older infrastructure, which serves a huge fraction of the East Coast, hangs from poles that are themselves vulnerable to falling trees. Once an outage starts, restoration takes time. The first step is always assessment. Crews cannot fix what they cannot find. They have to drive every affected road, identify every broken line, every fallen pole, every blocked access point. In the immediate aftermath of a major storm, those roads are often impassable due to debris. The second step is triage. Critical infrastructure comes first. Hospitals, water treatment plants, police and fire stations, major transportation hubs. After that, the largest population centers get priority. Last to be restored are typically the smallest, most rural neighborhoods at the end of long distribution lines. That ordering makes sense from a utility perspective. It also means that the people in the most exposed locations often wait the longest for power to come back. A week without electricity is not unusual. 2 weeks happens. In extreme cases, isolated rural areas have waited 3 weeks or longer. The cascading effects of a major outage go far beyond the obvious. Refrigerated food spoils within hours. Sump pumps stop working, allowing basements to flood. Heating systems fail just as the post-storm cold front arrives. Cell phone networks degrade as backup batteries at tower sites run down. Traffic lights stop working, creating dangerous intersections. For people on home medical equipment, an extended outage is a life-threatening emergency. Oxygen concentrators, ventilators, refrigerated medications, powered wheelchairs. Each requires reliable electricity, and backup batteries typically last only a few hours. Emergency managers across the affected states are activating their power outage protocols. Warming centers and cooling centers are being identified. Hospitals are reviewing their backup generator status. Pharmacies are stockpiling medications that cannot be refilled remotely if the grid goes down. The grid itself is more resilient than it used to be. Smart meters can identify outages without customers having to call. Automated switches can isolate damaged sections and reroute power around them. Drone technology is being used to inspect lines after the worst of the storm has passed, before crews can safely reach the area on foot. But all of that helps with restoration speed, not with prevention. When a tree falls on a line, the line still goes down. When a pole snaps, the pole still has to be replaced. The next several days are going to test every layer of the regional grid. Some neighborhoods will lose power for hours, some for days, a few for longer. By Wednesday, the news cycle will be full of restoration estimates that keep getting pushed further into the future. The lights are going to go out across a wide area. The question is how many of them, and for how long. Last August, a hurricane named Erin spun up in the Atlantic, never made landfall, and still managed to destroy houses in North Carolina. That paradox is the lesson coastal forecasters keep returning to. A direct impact to land can occur even if a storm doesn't make landfall. It can also include tropical storm-force winds reaching land, flooding rain from a storm just offshore, or a storm surge of at least 2 feet along the coast. Hurricane Erin is a prime example of a high-impact storm that didn't make landfall. Erin tracked offshore. The eye stayed hundreds of miles from the coast. Local meteorologists in Virginia and the Carolinas told residents the storm would not be a direct threat. Most people interpreted that as meaning it was not a problem. It was a problem. Wave heights along the Atlantic shore reached more than 15 feet at the peak of Erin's passage. Battering surf chewed away at the dune line for days. Storm surge of 3 to 4 feet pushed water into yards that had not seen flooding in decades. By the end of the event, multiple homes along the outer banks had collapsed into the ocean. Beach erosion stretched up the entire seaboard. Property damage estimates climbed into the hundreds of millions of dollars, all from a storm that never crossed the coastline. The Erin lesson applies directly to the current situation. The bomb cyclone forming offshore right now is unlikely to make a traditional landfall in the way a hurricane does. There may be no clear point where the center of low pressure crosses from water to land. The storm may track offshore for its entire life cycle, pulling away into the open North Atlantic before fully unwinding. That offshore track does not mean the storm stays offshore in its impacts. The wind field, the wave field, and the rain shield of a major bomb cyclone extend hundreds of miles from the center. Communities along the entire eastern seaboard from the Carolinas to Maine are within range of significant effects. Even though none of them will see the actual storm center make landfall, the Erin pattern is repeating. Coastal forecasters are doing their best to communicate that staying offshore does not mean staying harmless. Beach communities are being told to prepare regardless of the technical landfall question. Whether the message is being received is another matter. Decades of public messaging around hurricanes have trained people to think in terms of landfall location. If the storm is going to hit somewhere else, my area is fine. That mental model is dangerously oversimplified. For coastal storms, the relevant question is not where the eye crosses land. The relevant question is where the strongest wind field reaches, where the wave train arrives, where the surge piles up, and how long all of those effects persist. For this storm, the answers stretch from Hatteras to the Bay of Fundy. The Outer Banks are particularly nervous. After Erin, multiple homes that survived last summer are in even more precarious positions now. The dunes that protected them have been thinned by every storm since. The beach in front of them has narrowed. The elevation difference between the floor of those houses and the high tide line has shrunk. Some of those homes will not survive this storm. Property owners know it. The communities know it. The decisions about whether to even attempt protection are being made in real time. In some cases, owners have already moved everything valuable out and walked away. What separates this storm from Erin is the season. Erin was a tropical system fed by warm summer water. The current bomb cyclone is fed by the temperature contrast between cold Canadian air and warm Atlantic water. The fuel is different. The track is different. The result is the same. Coastal damage along a wide stretch of shoreline, beach erosion that takes years to recover from, homes lost to a storm that never officially made landfall. The Erin lesson is being learned again. Whether it sticks this time is up to the forecasters, the residents, and the slow process of memory. Storms get forgotten quickly. Damage takes longer to forget. But the next storm always seems to find a coast that has stopped paying attention. This time, the coast is paying attention. Most people think of the ocean as the surface, the part you can see, the part that reflects the sky and gives off the smell of salt. The ocean is far more than its surface. It is layers. Each layer holds different temperatures, different salinities, different pressures. Heat does not just sit on top. It penetrates downward, sometimes hundreds of feet, building up reserves that nobody can see from the air. Those reserves are what scientists call ocean heat content, and ocean heat content along the eastern seaboard has been quietly growing for decades. The surface temperature you see on satellite images tells only part of the story. A storm passing over warm surface water does not just feed on the top few inches. Strong winds churn the upper ocean, mixing the surface layer with deeper water. If the deeper water is also warm, the storm keeps drawing energy from below. If the deeper water is cold, the surface cools quickly and the storm starves. Modern measurements have shown that the upper 400 feet of the North Atlantic, off the east coast, is now significantly warmer than it was a generation ago. That warmth represents an enormous reservoir of energy waiting for the right storm to come along and tap it. The current bomb cyclone is going to tap quite a bit of it. When the storm's wind kicks up to hurricane force across the warm sector, the surface water churns. Cold water from below should rise to replace it. In a normal year, that cooler subsurface water would weaken the storm by reducing the heat available at the surface. But in the current state of the Atlantic, the subsurface water is not as cool as it used to be. The mixing brings up water that is still warm enough to keep feeding the storm. The cooling effect that would normally slow intensification gets muted. That is why some of the most explosive bomb cyclones in recent years have appeared to defy traditional limits. The storms have access to fuel reserves that earlier generations of meteorologists did not have to account for in their forecasts. The implications go beyond any single storm. As ocean heat content continues to rise, the upper limit of what storms can achieve gets quietly raised along with it. A bomb cyclone in 2026 has more available energy than a bomb cyclone in 1996 would have had under similar atmospheric conditions. The increase is gradual. Year over year changes are small. Decade over decade changes are noticeable. Half-century changes are dramatic. For the storm currently developing, the immediate effect is a higher ceiling. The original computer model forecasts may have been wrong precisely because the models were calibrated on data from earlier decades when ocean heat content was lower. As models update their reference points, the forecasts will get better. In the meantime, storms keep outperforming what the models initially predict. This is not theoretical. Forecasters track this pattern in real time. The phrase rapid intensification has become more common in operational discussions over the past decade. Storms that would have been slow developers in the past are now exploding. Storms that would have peaked at moderate strength are now reaching extreme strength. Every winter and every spring, the same coast that has always been a bomb cyclone factory now produces somewhat stronger bombs than it used to. Most of the increase happens quietly, year by year, without anyone noticing. The current storm will not be a record breaker, probably. Forecasters are not yet using language that would suggest a once-in-a-generation event. But it will be stronger than the original models predicted. It will deepen faster than the old forecasts said it could. It will draw on energy from a warmer ocean than the textbooks were written for. When the post-storm analyses are done in a few weeks, the meteorologists writing them will look back at the satellite imagery, the buoy readings, the sea surface temperature charts. They will see what they always see: a storm that overperformed its initial forecast, a storm that bombed harder than the models thought possible. They will write up their findings, and they will quietly add another data point to the long, slow chart of how the ocean beneath us is changing. And the next storm, whenever it comes, will start from a slightly higher baseline than this one did. The heat is there, the storms are finding it, the forecasts are catching up, slowly, ready for chapters 18 to 33 when you are. Every season has a personality. Spring on the East Coast usually means melting snow, blooming dogwoods, baseball games, and the occasional thunderstorm rolling through on a warm afternoon. The spring of 2026 has been something else entirely. The pattern started early. Severe thunderstorms have produced tornadoes, giant hail, destructive winds, flash flooding, power cuts, and battered homes. Affected areas include Texas, Oklahoma, Missouri, Wisconsin, Illinois, Mississippi, the wider plains, and especially the Midwest. The intensity caught a lot of people off guard. Spring storms are supposed to come in waves, with breaks between them long enough for communities to clean up. This year, the breaks vanished. One of the most conspicuous examples came in north and central Texas between April 24th and April 29th, when severe storms struck for 6 consecutive days. 6 straight days of severe weather. Towns that took a hit on Friday were taking another hit on Tuesday. By the end of that week, debris from the first round of storms was being thrown around by the third round. Insurance adjusters could not keep up. Power restoration crews could not keep up. Federal disaster aid teams could not keep up. The pattern that produced those Texas storms is the same pattern feeding the current East Coast system, a persistent jet stream configuration. A blocky atmospheric setup that locks weather features in place. Cold air repeatedly diving south to clash with unusually warm Gulf moisture. What makes 2026 different from a typical year is not necessarily the existence of severe weather, it is the consistency. Storm after storm, outbreak after outbreak, region after region. Each time the pattern resets, it seems to come back stronger rather than weaker. Meteorologists studying the pattern have offered several explanations. One involves the position of major upper-level features, which have been parked in unusually persistent locations. Another involves the temperature gradient between the unusually warm subtropical Atlantic and the still cool Canadian Arctic. A third involves changes in the jet stream's average path, which has been displaced south of normal for stretches of the spring. Whatever the cause, the result is a country that has been beaten up by severe weather almost continuously since March. Tornadoes have struck communities that rarely see them. Hailstorms have produced stones the size of softballs. Straight-line wind events have flattened forests across multiple states. Hailstones reached about 5 inches across in parts of Missouri this spring. 5 inches is the size of a grapefruit. A grapefruit falling from 20,000 feet at terminal velocity is a small bomb. It can break through windshields, dent metal roofs, and cause serious injury to anyone caught outside. The current storm offshore is the latest entry in a season that does not seem to want to end. The list of weather events that have already occurred reads like a year's worth of activity compressed into 10 weeks. For coastal residents who have been watching the inland chaos with sympathy but distance, the current storm changes the calculus. The pattern that has tormented the central states is now turning toward the Atlantic. The same atmospheric setup that produced the Texas hailstorms and the Midwest tornadoes is now feeding a coastal cyclone. The pattern itself is the story. Single storms are remembered as events. A pattern this persistent gets remembered as a season, and the season is not over. What forecasters fear most is that the pattern continues into hurricane season. If the same atmospheric configuration that has driven the spring chaos persists into June, the early part of the Atlantic hurricane season could be unusually active despite official forecasts calling for a below-average year. Patterns like this have a way of breaking just when forecasters expect them to continue, or continuing just when forecasters expect them to break. Either way, the next several months are going to be watched closely by every weather agency on the eastern half of the continent. Right now, the focus is on the bomb cyclone offshore. After that, attention turns north and east, watching for what comes next. Storms behave differently depending on what is happening above them. Most of the time, the upper atmosphere has a steady west to east flow that pushes weather systems along at a predictable pace. Storms form, intensify, peak, and then drift away over the next region. The whole life cycle takes a few days. The current bomb cyclone is not getting that kind of treatment. Sitting over eastern Canada is a closed upper-level low, a swirl of cold air at high altitude that has parked itself in place and refuses to move. The closed upper-level low over eastern Canada will continue to support a mean long-wave trough extending into the eastern US. Through the period, this pattern will bring a mature and persistent cyclonic circulation aloft and multiple shortwave energies to approach the base of the mean trough from upstream. That technical language describes a problem. A stalled upper-level low changes everything for the storm developing below it. Normally, a coastal cyclone would move along the eastern seaboard, peak in intensity over the New England coast, and then accelerate out into the open North Atlantic toward Iceland and Greenland. The whole journey takes maybe 2 days. With a blocking upper-level low overhead, that journey gets delayed. The storm cannot escape east as quickly. It tends to hang around, sometimes pulling north and stalling, sometimes wandering in unpredictable ways. A stalled storm does more damage than a moving one. The same areas get pounded for longer. Wind impacts double. Rain totals double. Surge cycles repeat over multiple high tide events. Communities that thought they had survived find themselves taking another round. The closed low over Canada is also feeding the storm. It does this by providing the upstream impulses that intensify the surface system. Each new shortwave energy that arrives at the base of the trough enhances the upper-level support over the storm. That additional support keeps the chimney effect strong, keeps the storm energized longer than it would otherwise be. For meteorologists, this is a known and unwelcome combination. They have a name for it. They call it a captured cyclone. The surface storm is captured by the larger upper-level pattern and cannot break free until the larger pattern breaks down. Larger patterns can take a while to break down. Sometimes days, sometimes a week. The question for everyone in the path of the current storm is how long the capture will last. If the upper-level low over Canada starts to weaken or move within the next 36 hours, the surface storm will be released to track normally out to sea. Impacts would be severe but limited to the typical 36 to 48-hour window. If the upper-level low holds on longer, the surface storm could linger near the coast for 2 or 3 days. Impacts would be far worse. Areas already weakened by the first day of wind and rain would face a second day of the same. The damage curves are not linear. 24 hours of hurricane-force wind does serious damage. 48 hours of hurricane-force wind does catastrophic damage. There is some indication in the latest model runs that the closed low over Canada will weaken slowly. Slowly is not fast enough for the coast. The surface storm is expected to remain in the mid-Atlantic and New England zone for at least 36 hours, possibly longer. During that time, it will continue to deepen, peak, and only slowly begin to weaken before finally being released to drift northeast. The geography of where the storm stalls. If it parks over the mid-Atlantic, the heaviest impacts hit Virginia, Maryland, Delaware, and New Jersey. If it drifts north and stalls over southern New England, the worst impacts hit Connecticut, Rhode Island, and Massachusetts. Either scenario produces serious damage. The exact distribution depends on where the upper-level pattern lets the surface low rest. Forecasters are tracking the upper-level features as carefully as the surface ones. The closed low over Canada is the puppet master. The surface bomb cyclone is the puppet. Until the puppet master moves, the puppet is not going anywhere. And right now the puppet master is sitting still. In meteorology, when rain bands repeatedly pass over the same towns one after another, it is called training, like train cars on a track. Each car identical to the one before it, each car bringing more of the same. Training rain bands are how moderate storms become disasters. A single rain band passing over a town drops maybe an inch of rain in 30 minutes. Annoying. Possibly enough to flood a few low-lying spots. Manageable. A second rain band right behind it drops another inch on already saturated ground. The drainage systems are now overwhelmed. Streets start to fill. A third rain band drops another inch. Now the streets are rivers. Cars are floating. Basements are filling. Storm drains have backed up because the system below them cannot accept more water. A fourth and a fifth band keep coming, each one identical to the last. The town is no longer dealing with rain. It is dealing with a slow-motion flood. The current storm has the potential to set up training rain bands over multiple coastal regions as it approaches the east coast and stalls. The bands would rotate around the storm's center, but if the storm itself is not moving forward, the same arms of intense precipitation could pass over the same towns repeatedly. Forecasters are watching specific zones with particular concern. The coastal Carolinas could see training along the Gulf Stream. Warm air rising from the warm water creates intense convection that can lock in over coastal counties. Rainfall rates of 2 to 3 inches per hour are possible if a band sets up correctly. The Delaware Bay region is another concern. The geography of the bay funnels moisture inland, and the surrounding terrain encourages rain to repeatedly fire over the same low-lying areas. Communities along the Delaware shore have flooded multiple times in recent years from similar setups. The Long Island and southern Connecticut shoreline could also see significant rain. The combination of onshore wind, shallow water, and dense urbanization creates conditions where flash flooding can develop rapidly, even without extreme rainfall totals. The threat extends inland. Cities like Philadelphia, Trenton, Hartford, and Providence are all in zones where training bands could deliver several inches of rain over a 6 to 8 hour window. Urban flooding in those cities has the potential to overwhelm storm drainage that was never designed for the kind of rainfall rates that bomb cyclones can produce. The hydrology gets worse from there. Each of those cities sits along a river system that drains a much larger upstream watershed. As rain falls across the entire watershed, water flows downhill into the rivers, which then push back through the cities on their way to the ocean. The combination of direct urban rainfall and incoming river flow can flood neighborhoods even if the immediate rain stops. For neighborhoods near the coast, the river flow has nowhere to go. Storm surge from the ocean blocks the river's mouth. Fresh water cannot drain. Salt water cannot retreat. The system locks up. This is the compound flooding scenario that makes hydrologists wake up at night. Several of the most vulnerable river systems are already running high from earlier spring rain. Soil moisture across the region is well above average. Reservoirs are near capacity. The natural sponges that would absorb rainfall in a typical storm are already saturated. That means the runoff fraction is going to be unusually high. Instead of half of the rain soaking into the ground and the other half running off, a much larger share will run off immediately. The streams will rise faster, the rivers will crest higher, the flood gauges will hit warning levels sooner than they would in a drier year. Forecasters at river forecast centers across the affected region are coordinating with National Weather Service's offices, emergency managers, and state agencies. River forecasts are being issued and updated. Expected crest levels are being communicated to communities along the path of expected high water. Evacuation contingencies are being reviewed. The training rain has not started yet. The storm has to organize and stall first, but the setup is in place for it to happen. And when training rain hits a region that is already saturated, the results can be measured in feet of water above the highest expected flood line. Where the trains run, the towns drown. A bomb cyclone is not always a single low-pressure system. Sometimes it spawns secondary systems that develop along its trailing edges or within its broader circulation. When that happens, the situation gets complicated. The phenomenon is called secondary cyclogenesis, and it adds another layer of unpredictability to what is already a difficult forecast. The original storm continues on its track, but a new storm forms along the periphery, often farther south or east, and starts intensifying on its own. Communities that were on the edge of the original storm's impact zone can suddenly find themselves directly under a brand new system that nobody mentioned in the morning forecast. Secondary cyclogenesis tends to happen when the original storm has plenty of available energy to give away. A weak storm cannot spawn another storm. A powerful storm can. The current bomb cyclone has all the ingredients to become a parent system, with multiple smaller features potentially developing along its edges. Forecasters watch for several signatures. The first is wave development along the trailing cold front. As the front sweeps offshore behind the parent storm, kinks can develop where conditions favor a new low. Each kink is a candidate for secondary development. Most fizzle. A few mature into independent systems. The second is a process called trough merger. Sometimes a separate area of upper-level energy approaches from upstream while the parent storm is still active. If the merger happens cleanly, the parent gets reinforced. If it happens messily, the trailing energy can break off and spin up its own surface low. The third is feedback from the warm sector. Intense thunderstorm clusters within the storm's warm air mass can sometimes organize their own circulation, especially over warm water. Mesoscale convective vortices, or MCVs, are small but capable of growing into significant features under the right conditions. For the current storm, the secondary risk is highest along the trailing front as it sweeps southeast through the Atlantic. A new low could potentially form along the front, somewhere south of the parent system, possibly affecting parts of the southeast Atlantic coast or producing high seas across the offshore shipping lanes. that everyone thought was south of the worst weather. There is also a concern about secondary development to the east. As the parent storm starts to weaken near the end of its life cycle, an upstream impulse approaching from the upper Midwest could force a new low to form near the original system's location. The result would be effectively two storms in rapid succession. A double storm scenario doubles the impact window. Areas that absorbed the first round of damage have to face a second round before they have time to recover. Power restoration crews who are just getting started have to retreat. Coastal residents who began the cleanup process have to evacuate again. That kind of 1-2 punch is what coastal forecasters dread most. Single storms can be planned for. Single storms have a clear beginning and end. Storms that come in pairs or that linger and reform create open-ended impact windows that emergency managers cannot easily resource. The current model runs are not yet showing a clear secondary cyclone scenario for this storm. But the ingredients are present. The parent system has plenty of energy. The trailing front is sharp. The upper-level pattern continues to feed disturbances into the region. Forecasters are watching closely. If a secondary develops, the warning timeline could be extremely short. Surface lows can form and intensify in hours when conditions are right. The lead time between first identification and significant impacts could be less than a day. For coastal communities, the prudent assumption is that the storm currently approaching is the start of a multi-day weather situation, not a single discrete event. Even if no clear secondary develops, the broader weather pattern is going to be disturbed for an extended period. Showers, thunderstorms, gusty winds, and elevated wave activity are all likely to persist after the bomb cyclone itself has weakened. The story of any major coastal storm rarely ends with the storm. It ends with whatever follows. And what follows the current system is uncertain in a way that ought to keep everyone paying attention beyond the worst of the impacts. Long before most coastal residents have heard about a developing storm, the working mariners are already moving. Commercial fishing fleets, offshore wind crews, coastal cargo vessels, and ferry operators all watch the marine forecasts continuously. They have to. A bad call about an offshore storm can cost lives, vessels, and millions of dollars in equipment. The decisions about whether to head out or stay in are made in the pre-dawn hours, often days ahead of the public's awareness of the threat. For the current bomb cyclone, the marine community started reacting on Friday. The NWS Ocean Prediction Center issued storm warnings for offshore waters with forecast winds reaching 110 kilometers per hour and seas building up to 7 m. Translated to American units, that is wind gusts approaching 70 miles per hour and waves climbing to 23 feet. 23-foot seas are the kind of conditions that can capsize smaller commercial vessels and force even large container ships to alter course. Fishing fleets working the Carolinas and Mid-Atlantic shelf began hauling gear and steaming for shelter on Saturday. The closer harbors on the inland side of Barrier Islands started filling up. Larger vessels capable of riding out heavy seas at sea decided whether to do that or to commit to a long run for a deeper port. The wrong choice could mean being caught in the middle of the storm. Offshore wind construction in the New York Bight and along the New England coast paused operations. Workers on platforms were either evacuated or sheltered in place depending on the position of the platforms relative to the storm track. Crew transfer vessels returned to port. Cable-laying ships moved out of the way. Ferry routes between the mainland and the islands started planning for cancellations. Martha's Vineyard, Nantucket, Long Island ferries to Connecticut, the various Maine coastal ferries, all began coordinating on which crossings would be the last ones before the suspension and which would be the first ones after. Cargo terminals along the east coast started battening down. Container stacks were lowered where possible. Cranes were locked in their stowed positions. Loading operations were either accelerated to clear ships before the storm or paused entirely. The Coast Guard set port conditions accordingly. Captain of the port orders went out from various district offices, restricting vessel movements, requiring anchorage shifts, and in the most exposed ports, ordering all transient vessels to leave. The mariner community has its own version of warning levels. There is a category called gale with sustained winds in the upper 30s to lower 40s of miles per hour. There is storm with sustained winds in the upper 40s through low 60s. And then there is hurricane force, where sustained winds exceed 73 miles per hour. Hurricane force conditions in offshore waters require the most extreme preparation. Fishing fleets rarely operate in those conditions. Cargo ships try to alter course to avoid them. Cruise ships, where possible, cancel itineraries entirely. The current storm is forecast to produce hurricane-force gusts, possibly approaching hurricane-force sustained winds in the worst stretches. That is far above the threshold for normal commercial operations. For the offshore wind industry, which has been growing rapidly along the east coast over the past several years, this storm is a real test. Most of the existing turbines are designed to survive winds far stronger than what this storm will produce. But supporting infrastructure, including cable systems, substations and crew transfer vessels, has more variable design margins. Any damage to subsea cables would be expensive to repair and could leave the affected wind farms offline for months. The shipping lanes that connect the east coast to Europe pass directly through the area where the storm is expected to deepen. Ships in transit have several options. Some will divert north toward Iceland to skirt the worst of the system. Others will divert south to ride out the storm in better conditions. A few unlucky ones will not be able to avoid the worst of the storm entirely and will simply have to ride it out, with crews secured below decks and engines running just enough to maintain headway against the wind. By the time the storm peaks over the weekend, the mariners who could move have moved. The ones who could not are bracing. The ocean ahead of them is going to do what bomb cyclones make oceans do. It is going to come alive in ways that landlubbers cannot quite imagine. 23-foot seas, sustained gale force winds, visibility down to a few hundred yards in driving rain. For the people who make their living on that water, this is the kind of storm that gets talked about for the rest of their careers. Most people never see a weather chart that was actually designed for a sailor. They see the colourful television maps with little raindrops and animated suns. They see smartphone apps with prettily formatted forecasts. They see social media posts with sensational headlines. Mariners look at something different. They look at surface analysis charts produced by the Ocean Prediction Center, pressure isobars, wind barbs, wave height contours, frontal symbols. The charts are dense, technical, and almost monochrome. To an untrained eye, they look like something from an engineering textbook. To a mariner, they are the difference between a safe trip and a disaster. The Ocean Prediction Center is one of the most underappreciated forecasting offices in the federal weather system. It produces marine forecasts for vast stretches of the Pacific and Atlantic, providing the technical guidance that commercial fleets, military vessels, and offshore industries depend on. Its charts are issued every 6 hours. Its forecasts extend out to 4 days. For the current storm, the Ocean Prediction Center has been issuing escalating products since early in the week. Each new chart has shown the deepening low intensifying further, the wind field expanding wider, the wave heights climbing higher. The language used in marine forecasts is precise and unforgiving. There is no fluff, there is no qualifier to soften the message. The text reads like an engineering specification. A typical forecast statement might read, storm warning for waters from 40 north to 35 north between 65 west and the Gulf Stream. Winds 25 to 40 knots becoming 45 to 55, with gusts to 70 by Sunday night. Seas building to 17 to 23 feet. That single sentence tells a mariner everything they need to know: where the bad weather will be, when it will arrive, how strong the wind will get, how high the seas will build. There is no attempt to downplay or sensationalize, just numbers, just isobars, just wind barbs. The mariners reading those forecasts make decisions accordingly. Where can they shelter? How much fuel to carry, whether to deploy emergency equipment, when to issue distress calls if they end up in trouble. For the current storm, the Ocean Prediction Center's wave height forecasts have been particularly significant. 20-foot seas can capsize smaller vessels. 25-foot seas are dangerous to anything under about 100 feet long. 30-foot seas can overwhelm even large ocean-going ships if the angle of attack is wrong. The peak wave forecasts for this storm have been climbing through the week. Initial estimates of 15-foot peak seas have been revised up to 23 feet, then in the worst-case scenarios, up to 27 feet over the offshore mid-Atlantic. 27-foot seas are not a small boat problem. They are an everyone problem. The chart-making art is also worth understanding. Surface analysis charts use a standard set of symbols that have remained essentially unchanged for nearly a century. A solid line is an isobar, a contour of equal pressure. The closer the lines, the stronger the wind. A line of triangles is a cold front. A line of half circles is a warm front. Combinations of triangles and half circles indicate occluded fronts and other complex features. Wind barbs show direction and speed. Each long feather is 10 knots. Each short feather is 5 knots. A solid triangle is 50 knots. The barbs cover the chart like little arrows, showing exactly where the wind is blowing and how fast. For an experienced mariner, reading one of these charts is like reading a sentence. The pattern of isobars, the placement of fronts, the values of pressure at the storm centers, all combine to tell a story about what the next few days will bring. The current chart for this storm tells a very specific story. It shows a deep low with tightly packed isobars indicating extreme winds, sitting just off the New England coast. The trailing cold front extends southwest toward Florida. The warm front extends east into the open Atlantic. The peak central pressure is forecast to drop to numbers that make experienced eyes widen. Mariners reading that chart will not need a television anchor to tell them this storm is serious. The chart speaks for itself, in the silent technical language that has guided sailors through bad weather for generations. The chart says stay home. The chart says find harbor. The chart says wait this one out. The mariners are listening. The current storm is happening in early May. Hurricane season officially begins June 1st. Those two facts are not independent of each other. Bomb cyclones in the spring are not the same kind of storm as hurricanes in the summer. They have different fuel sources, different structures, and different impact patterns. A bomb cyclone draws energy from temperature contrasts in the atmosphere. A hurricane draws energy almost entirely from warm ocean water. The two systems are meteorological cousins, but not twins. Yet they share an ocean, and what one storm does to that ocean affects what the next storm can do to it. When the current bomb cyclone churns the water along the Gulf Stream, it mixes the warm surface layer with cooler water below. That mixing should leave the upper ocean slightly cooler in the immediate aftermath of the storm. In a normal year, that cooler water would persist for a few weeks before the late spring sun reheated the surface. In the current Atlantic, the picture is more complicated. The deeper water that gets mixed up to the surface is not as cool as it used to be. Ocean heat content has risen. The cooling effect from a major storm passage is muted. Within a week or two, the surface is back to where it started, sometimes warmer, depending on solar heating and ocean current conditions. That has implications for the upcoming hurricane season. El Niño is expected to develop and strengthen, which should help keep the season near to below the historical average. The forecast calls for 11 to 16 named storms, including 4 to 7 hurricanes and 2 to 4 major hurricanes. It is not. The historical record is filled with low-count seasons that produced individual storms of catastrophic strength. The 2025 hurricane season was close to the historical average in terms of the number of storms, but it featured 3 Category 5 hurricanes, just one shy of the all-time record of 4. 3 Category 5 storms in a single season is a remarkable record. Those storms reached the highest possible classification on the hurricane scale. Each one had the potential to reshape coastlines if it came ashore in the wrong place. The total storm count was average. The intensity was historic. That pattern, average count with extreme intensity, is what forecasters are increasingly worried about for the coming years. Warmer oceans tend to produce stronger storms, even when atmospheric conditions limit the total number of systems that can form. The high end of the distribution gets pushed higher. For coastal residents, that translates to a simple observation. The forecast number of storms matters less than the strength of the storms that do form. One major hurricane can do more damage in a single landfall than 10 weaker storms combined. The current bomb cyclone is, in a sense, a preview of what the warm ocean is capable of supporting. It is using the same heat reservoir that the first tropical storms of the season will tap. It is exposing the same coastal vulnerabilities that hurricanes will test in a few months. The Outer Banks erosion that this storm causes will not heal before hurricane season starts. The damaged dunes will still be damaged. The structures that survive this storm in compromised condition will face the next storm in even worse shape. The cumulative effect of a strong spring storm followed by an active hurricane season can be devastating for individual communities. Federal disaster officials are already thinking ahead. The current storm is going to require resources. Hurricane season is going to require more. The federal disaster response system has only finite capacity. A particularly active spring eats into the resources available for summer and fall events. State emergency management agencies face the same constraint. Stockpiled supplies that get distributed for the current storm have to be replenished before the next event. Mutual aid agreements that activate now have to be honored later. Trained personnel who deploy this week need rest before they deploy again in July. The current storm is the first big test of the system in 2026. It will not be the last. The water that fed this storm is still out there. It is waiting for the next pattern to deliver the next event. And by the time hurricane season is fully active, the same coast that is about to take a beating from a spring bomb cyclone could be facing tropical systems pulling energy from the same warm Atlantic reservoir. The question is not whether more storms are coming, the question is whether the coast can absorb them all. Every spring, the major hurricane forecasting agencies issue their pre-season outlooks. The numbers get headlines. The headlines get repeated. By the time hurricane season actually starts, most coastal residents have absorbed a vague sense of whether this is supposed to be a busy year or a quiet one. The vague sense is dangerous. Although the forecast points to fewer storms, the NOAA and industry data make one thing very clear. Hurricane risk has not decreased, it's become more concentrated and less predictable. That observation comes from the restoration industry, the contractors who clean up after disasters. They see the actual damage, not the storm counts. And what they see does not match the comforting narrative of below-average forecasts. Several of the worst hurricane events in modern history have come during seasons that were forecast to be quiet. The reasons are simple. A single storm hitting a vulnerable coast can produce more damage than an entire active season hitting empty stretches of ocean. The metric that matters is not how many storms form, it is which storms reach which coasts. For the current spring storm, the same principle applies. The storm has not been called catastrophic in the headlines. It has not been classified as historic. The official messaging has been measured. But the actual impacts may be far more significant than the messaging suggests. This is a common pattern in modern weather communication. The forecasts focus on quantitative thresholds, wind speeds, pressure values, rainfall totals. When a storm falls just short of a category boundary or just below a record, it tends to get described in moderating language, significant but not historic, strong but not catastrophic. The actual people in the path of the storm rarely care about category boundaries. They care about whether their roof stays on, whether their basement floods, whether the power stays on, whether their elderly neighbor can get to the hospital if a medical emergency happens during the storm. A storm that ranks just below the historic threshold can still take down trees, knock out power, flood roads, and trap people in their homes. The impact is no less real because the official label is not the worst possible one. There is also the question of cumulative damage. When hurricane behavior sets the tone, there is no such thing as a quiet season. The same point applies to spring storms. A region that has already absorbed several smaller weather events in the preceding weeks does not have full resilience left when a moderate storm arrives. The 2026 spring storm season has been, by any measure, brutal. The current bomb cyclone is arriving on top of weeks of severe weather that has already strained emergency response systems, damaged infrastructure, and exhausted the patience of the affected communities. The cumulative dimension is rarely captured in forecasts. A storm forecast in isolation looks manageable. The same storm, in the context of the year that preceded it, looks much worse. Roofs that were marginal before are now leaking. Trees that were stressed are now ready to fall. Power infrastructure that was patched together after the last storm is now ready to fail again. Forecasters know this. They include it in their internal discussions. They flag it in coordination calls with emergency managers, but it rarely makes it into public messaging in a way that hits home. The danger of a quiet forecast is that it gives people permission to ignore preparation. If the storm is supposed to be moderate, they think, why bother bringing in the patio furniture, charging the backup batteries, filling the gas cans, or topping off the prescription medications? When the moderate storm overperforms, the unprepared are caught flat-footed. For the current bomb cyclone, the official messaging has been climbing all week. Saturday's coordination calls produced more urgent language than Friday's. Sunday's forecasts have included impact statements that were not in Saturday's products. By Monday morning, the messaging is likely to be considerably stronger than the original Friday outlook suggested. But the early outlook is what most people remember. By the time the messaging catches up, the storm is too close to the coast for comprehensive preparation. The hurricane season ahead carries the same risk. A below-average forecast is not a guarantee of a quiet season. It is, at best, a probability statement about the total number of storms. It says nothing about which storms will form, where they will track, or how strong they will become. Coastal residents who use the forecast as a reason to skip preparation are gambling with the wrong information. The forecast is not a description of what will happen to them. It is a description of what will happen to the basin as a whole. The basin is large, their house is small. The match is uneven, and the forecasts almost never tell them which way it will fall. Off the east coast of the United States, somewhere over the central Atlantic, sits a permanent high-pressure system called the Bermuda High. It does not move much. It does not change its essential character. It sits there year-round, like a giant atmospheric boulder that determines where storms can and cannot go. The Bermuda High is one of the most important features in East Coast weather, and most people have never heard of it. It is a semi-permanent high-pressure system that strengthens in summer and weakens in winter. Its position controls the prevailing wind patterns across the western Atlantic and the eastern United States. When the high is positioned a certain way, hurricanes track one direction. When it shifts, they track another. Small adjustments in its location can be the difference between a storm hitting Florida and a storm curving harmlessly out to sea. For the current storm, the Bermuda High position matters in a specific way. Another factor is the position of the Bermuda High. It may sit a bit farther south and east again this year, similar to last season. That setup can allow more storms to curve away from the US, especially in the western Atlantic. A south and east position for the high should, in theory, encourage storms to escape into the open Atlantic without raking the coast. That is the optimistic scenario for tropical systems later in the year. But the same Bermuda High position has different effects on extratropical systems, like the current bomb cyclone. Spring coastal storms tend to be steered by the same upper-level patterns that interact with the Bermuda High, but the relationship is more complicated than it is for tropical systems. The current upper-level pattern features a strong trough over the eastern United States, with the closed low over Canada anchoring the system in place. The Bermuda High, displaced south and east, is acting as a partial blocking feature against the storm's eastward escape. The combination creates the captured cyclone effect mentioned earlier. The storm cannot easily move out to sea because the Bermuda High is sitting in the path it would normally take. That is bad news for the coast. A storm that cannot escape east tends to track north along the seaboard, raking the entire coast as it goes, before finally being released into the open ocean somewhere off Newfoundland. The Bermuda High has another effect. It controls the moisture pipeline from the subtropics to the storm. The clockwise circulation around the high pulls warm, humid air from the Caribbean and Central Atlantic up toward the east coast. That moisture is what the current storm is feeding on, and the high's position is determining how generous the moisture supply is. For this storm, the moisture pipeline is wide open. The high's clockwise circulation is delivering tropical air to the warm sector of the cyclone. Each new pulse of moisture brings more energy, more rain, and more potential for intensification. Forecasters at the climate prediction centers track Bermuda High behavior continuously. Its position is monitored, its strength is measured, its evolution is projected. Small changes can have outsized impacts on what happens to the East Coast in the days ahead. The high is not the only steering feature, but it is one of the most consistent. While other atmospheric features come and go, the Bermuda High is always there in some form. Storms have to negotiate with it. Coastal weather has to be understood in relation to it. For the current storm, the negotiation is going badly. The high is in a position that traps the storm against the coast longer than it would otherwise be. The atmospheric chess game is favoring the storm over the coast. In a few days, the pattern will break. The Bermuda High will shift. The closed low over Canada will weaken. The storm will be released to track east into the open Atlantic, where it will eventually wind down. In the meantime, the coast has to absorb whatever the high will not let escape. And what the high will not let escape is a bomb cyclone with energy to burn and time to do its damage. The high will move, eventually. The storm will move, eventually. The damage by then will have been done. There is a window in every major weather event between when the forecast first identifies the threat and when the impacts arrive at the coast. That window is supposed to be wide enough for emergency preparations to happen. For rapidly intensifying storms, the window often closes before preparations are complete. This is the central operational challenge for modern coastal forecasting. Bomb cyclones intensify faster than warnings can scale up. By the time the warning is at the appropriate level for the actual threat, the storm is already too close for the full set of preparations to be implemented. The pattern is consistent across decades of major storms. The first warning is issued at one level of urgency. The actual storm exceeds that level. The warning gets upgraded. The next forecast period also exceeds the upgraded warning. Another upgrade happens. By the time the warning matches the storm is hours from impact. For the current bomb cyclone, the warning timeline started on Friday. Marine warnings were the first to escalate. Coastal flood watches followed. Wind warnings came next. By Saturday, multiple warning categories were active across the affected coastline. Each upgrade triggered a new round of preparations from emergency managers, utility companies, transportation departments, and individual residents. Each upgrade also represented a forecast that had previously been wrong in the sense that the original guidance had underestimated the threat. The compression of the warning timeline has real consequences. School districts that plan to be open are forced to close at the last minute. Transit systems that plan to operate have to suspend service abruptly. Commercial operations that did not anticipate disruption have to scramble. For individual residents, the compressed timeline means decisions get made under increasing time pressure, whether to board windows, whether to fill prescriptions, whether to evacuate, whether to travel home from a planned weekend trip. Each decision has different optimal timing, and a compressed warning window forces all of those decisions to be made nearly simultaneously. Some preparations cannot be completed in a hurry. Boarding plywood over windows takes time and labor. Securing yard items takes coordination. Topping off generators requires a trip to the gas station, which may already be sold out. Each of those tasks competes for time as the storm approaches. The most consequential decision is usually evacuation. For coastal areas in the path of severe storm surge, evacuation is the only reliable protection. Evacuation requires hours of packing, hours of driving, hours of finding lodging inland. If the warning comes too late, evacuation becomes impossible. For the current storm, evacuation orders have been limited so far. The storm is forecast to produce serious surge in some specific areas, but the surge zones are smaller than they would be for a major hurricane. Most affected residents will be sheltering in place rather than evacuating. That calculus could change quickly if the storm intensifies beyond the current forecasts. A few additional millibars of pressure drop could push surge predictions into evacuation territory for additional zones. The decisions about whether to issue evacuation orders are being made in real time, with forecast uncertainty as the dominant factor. There is a structural challenge in modern weather warning systems that the current storm illustrates well. Warnings are issued by official agencies based on quantitative thresholds. The thresholds are conservative, for good reason. False alarms erode public trust in the warning system, and overwarning has its own costs. But conservative thresholds also mean that storms which are about to exceed those thresholds may not trigger warnings until they actually exceed them. There is a built-in lag between storm intensification and warning escalation. For slowly evolving storms, the lag is manageable. For bomb cyclones, the lag can be catastrophic. The forecasting community has been working for years to reduce this lag. Probabilistic forecasts, ensemble products, plain language risk communication. All of these tools are designed to give emergency managers and the public earlier and more nuanced information about the range of possibilities. For the current storm, those tools have been deployed extensively. The official messaging on Friday already included language about potential rapid intensification. By Saturday, the language was more specific. Sunday's products are quite explicit about the worst-case scenarios. Whether the public has absorbed that messaging is another question. Probabilistic forecasts work poorly when most people are not weather professionals and rely on television anchors or social media for their information. The nuance gets lost in translation. The end result is that millions of people in the path of the current storm are getting their first serious look at the threat in the final hours before impact, even though forecasters have been talking about it for days. The warnings have been there, the hearing has been late, and the storm is not going to wait. When a storm is happening, the question of climate change always comes up. It also always gets dodged. The reason is partly scientific. Attributing any single storm to climate change is methodologically difficult. Climate is the long-term statistical pattern of weather. Any individual storm might or might not have happened in a different climate. The science of attribution has improved considerably in recent years, but it still operates on probabilistic statements rather than deterministic ones. The reason is partly cultural. Climate change is a politically charged topic, and meteorologists who are trying to communicate about an immediate threat often choose to avoid wading into broader debates. The job at hand is to keep people safe from the storm in front of them, not to argue about what shaped it. The reason is partly practical. The conversation about climate change tends to be long and involved, and the time available during a developing severe weather event is short. But the question keeps coming up because the storms keep getting worse, and people are noticing. Climate change adds another layer of concern. Meteorologists and scientists are still studying how warming affects tornado frequency. However, there is a fact that a warmer atmosphere can hold more moisture, which can intensify heavy rainfall and create more fuel for severe storm environments. The result is not always more tornadoes everywhere, but the atmosphere is increasingly loaded with ingredients that can make outbreaks more dangerous when conditions align. That same observation applies to bomb cyclones. The atmosphere can hold more moisture, the oceans hold more heat. The temperature gradients that drive storm intensification have shifted. Each individual storm forms and evolves according to local conditions, but the local conditions themselves are not what they used to be. The data on this is reasonably clear at the basin scale. Sea surface temperatures across the North Atlantic have risen significantly over the past several decades. Ocean heat content in the upper layers has risen even more. The warm sector air that feeds storms now contains more moisture per unit volume than it did a generation ago. Whether all of these changes have made bomb cyclones individually stronger is harder to answer with certainty. Some studies suggest that the most intense storms in a given basin tend to get more intense as the underlying conditions warm. Other studies focus on storm tracks, frequency, or duration. The picture is not yet complete. What is clear is that the conditions that bomb cyclones thrive in have all moved in directions that favor stronger storms, warmer water, more moisture, sharper gradients. The recipe for intense cyclones has more of every ingredient than it used to. Whether the current storm is a climate change storm in any meaningful sense is a question that researchers will study after the event. They will compare the actual conditions to historical analogues. They will run climate models with and without warming influences to see how the storm might have differed in a different climate. They will publish their findings in technical journals. Most of that analysis will be invisible to the general public. What the public will see is another major storm, another round of damage, another news cycle dominated by destruction, and another quiet sense in the back of many minds that this is happening more often than it used to. The frequency question is part of the puzzle. The intensity question is part of the puzzle. The track and timing questions are part of the puzzle. Each piece is being studied, and the picture that emerges is one of an atmosphere that is shifting in ways that affect coastal storms. For the residents of the East Coast, the science of attribution probably matters less than the practical reality of the storms themselves. Whether or not climate change made the current bomb cyclone slightly stronger than it would have been, the storm is still going to do whatever damage it does. The roof shingles do not care about attribution. The flooded basements do not care about probabilistic statements. What might matter more, in the long run, is whether the patterns continue. If bomb cyclones are reliably stronger than they used to be, coastal infrastructure designed for older storms will face accelerating stress. Flood maps based on historical data will be increasingly inadequate. Building codes calibrated to wind loads from previous decades will be insufficient for current conditions. The slow conversation about whether to update those standards is happening in technical agencies and engineering committees. It moves at the pace of bureaucracy, which is slow. The storms move at the pace of weather, which is fast. The two timescales are not converging. They are diverging, and that divergence is going to determine, more than anything else, whether the next several decades of coastal storms can be absorbed by communities that are already stretched thin. The question of climate change will keep coming up. The answers will keep being partial. The storms, meanwhile, will keep arriving. There is a subtle dance that controls the early Atlantic hurricane season. Most people have no idea it is happening, but the African continent has been participating in it for thousands of years. Every spring and summer, dust from the Sahara Desert gets lofted high into the atmosphere by strong winds. The dust forms a layer that drifts west across the Atlantic Ocean. Forecasters are also watching for periods of dry Saharan dust and changes in the flow of tropical waves coming off Africa. Those factors could, at times, slow development in the Maine area where storms usually form across the Atlantic. The Saharan air layer, or SAL, has multiple effects on Atlantic storm formation. It is dry, which suppresses the convection that storms need. It is dusty, which can interfere with cloud microphysics. It is associated with stronger upper-level winds, which tear apart developing storms before they can organize. For decades, the SAL has been a reliable governor on Atlantic tropical activity, Years with strong SAL tend to have less early season activity. Years with weak SAL tend to have more. The 2026 season is being watched carefully because the SAL behavior has been variable. Some periods have featured robust dust outbreaks, others have featured unusually clear air over the Maine development region. The variability adds uncertainty to seasonal forecasts. For the current bomb cyclone, the SAL is not directly relevant. Bomb cyclones get their energy from temperature contrasts, not from warm tropical water in the way that hurricanes do. Saharan dust does not affect their formation in any significant way, but the SAL matters for the broader weather pattern that the current storm is part of. Atmospheric moisture, dust, and aerosol concentrations all affect radiation balances at large scales. Persistent shifts in any of these can ripple through the entire weather pattern over the coming weeks. For the early hurricane season, the SAL has been described as still active but inconsistent. Periods of dust have been interrupted by periods of clear air. The clear air periods have been associated with active tropical wave trains coming off Africa, some of which have produced early season tropical disturbances even before the official June 1st start of hurricane season. The interplay is significant. If the SAL fades early, tropical activity could ramp up sooner than the official forecasts suggest. If the SAL remains robust through June, early season activity could be suppressed despite the warm ocean conditions that would otherwise favor it. The current bomb cyclone is going to leave behind some atmospheric disturbances that could interact with the early season tropical pattern. Trough remnants, frontal boundaries that decay over the open Atlantic, mesoscale features that can act as seed disturbances for later tropical development. The exact pathways are difficult to predict. Spring extratropical storms sometimes leave behind features that contribute to the first tropical storms of the new season. Sometimes they leave nothing significant. The connections are subtle and often only become clear in retrospect. What is clear is that the Atlantic Ocean is not a series of disconnected events. The current bomb cyclone, the early season SAL, behavior, the developing El Niño in the Pacific, and the projected hurricane season activity are all parts of a single coupled system. Changes in one element propagate through to the others over time. For coastal residents, the practical implication is that the current storm is not the end of weather concerns for the year. It is the beginning. The patterns that produce this bomb cyclone are setting up the patterns that will produce summer thunderstorm complexes, hurricanes, and fall extratropical events. The dust over Africa might seem unrelated to the storm off the Carolinas. They are, in fact, parts of the same system. The atmosphere is connected at scales that local weather rarely captures. When the bomb cyclone finally dissipates over the open North Atlantic in a few days, the energy it released will not vanish. It will be redistributed. Some will warm the upper atmosphere. Some will mix into ocean waters. Some will be carried by global circulation patterns to other parts of the planet. The hurricane season starts in 3 weeks. The conditions that will shape that season are being shaped right now, in part by the storm currently forming offshore. The handoff between spring and summer weather patterns is in motion, and the bomb cyclone is one of the major events of that handoff. Every major coastal storm exposes a difficult truth about American coastal development. We keep building in places where storms keep happening. We rebuild in those same places after storms damage them. And we are surprised every time when the next storm causes new damage in the same locations. The pattern is most visible on barrier islands. These narrow strips of sand sit just offshore along much of the east coast, providing some protection to the inland areas behind them, but also offering desirable coastal real estate. The barrier islands are inherently dynamic. They migrate, they erode, they grow in some places, and shrink in others. Building permanent structures on barrier islands is, in geological terms, a temporary undertaking. The island is not a stable foundation. It is a moving feature, and the structures placed on it have to be expected to lose their foundations eventually. Yet, the construction continues. Beachfront homes get built, sold, rebuilt after storms, and sold again. Each cycle, the line between building and water gets a little narrower. Each cycle, the federal flood insurance program absorbs some of the losses. Each cycle, the local property tax bases benefit from the high property values, which depend on the beachfront location. The current bomb cyclone is going to expose the unsustainability of some of these arrangements. Several specific homes along the most vulnerable stretches of the Outer Banks are unlikely to survive the storm. Photos and videos of their collapse will go viral. The same has happened after previous storms. The names of the destroyed houses become talking points for a few weeks. Local officials issue statements about the need for better planning. Property owners receive insurance settlements. New construction begins. A few years pass. New storm comes. New homes destroyed. The cycle has continued for decades. It is not unique to the East Coast. Similar patterns play out along the Gulf Coast, the Pacific Coast, and in flood-prone river valleys throughout the country. People want to live near beautiful natural features. The features are also natural hazards. The desire to live near them outweighs the awareness of the hazards, except briefly during and immediately after major events. There are policy options that could address the issue: stricter zoning, mandatory setback requirements, higher flood insurance premiums for the most exposed properties, buyout programs that purchase damaged properties from their owners and convert the land back to natural buffer zones. Most of these options are politically difficult. Coastal residents tend to oppose stricter regulations, particularly retroactive ones that might affect their existing properties. Political leaders are reluctant to push for policies that face strong local opposition. The federal flood insurance program has been criticized for years for subsidizing risky development, but reform efforts have repeatedly stalled. The economic costs of the current pattern keep rising. Each major storm produces billions of dollars in damage that has to be paid for somehow. Some of the cost falls on private insurance. Some falls on the federal flood insurance program. Some falls on direct disaster relief from federal, state, and local agencies. Some falls on the property owners themselves. Across the country, the cumulative bill for coastal storm damage has been climbing for decades. Adjusted for inflation, the trend is unmistakable. Even accounting for population growth and increasing coastal property values, the per capita damage from major storms has been increasing. Whether that trend can continue indefinitely is an open question. The federal disaster response system is funded year by year, and budget pressures are likely to grow as the cumulative cost of disasters grows. State and local emergency management agencies face the same constraints. Private insurance markets in the most exposed areas are already showing signs of stress, with some major insurers withdrawing from coastal markets entirely. The current storm is one event. The pattern that produces it is the larger story. As long as the pattern continues, the costs will continue to rise. Coastal residents who are watching the storm approach face the immediate question of how to protect their property and their lives. The longer-term questions about whether the property should have been there in the first place are harder to ask while the storm is still hours away, but those questions will keep coming up. After this storm, after the next, after the one after that, and eventually the answers will have to address the underlying pattern, not just the individual events. The storm is coming, the development is already there, the collision between the two is about to happen, again, for the latest in a long sequence of similar collisions. Inside the operational forecasting community, there is a quiet vocabulary of historical storms that get referenced during major events. The names function as shorthand. Mention them, and other forecasters know what you mean. January 2018, the Grayson Storm. A pressure fall of approximately 59 millibars in 24 hours, well beyond the latitude-adjusted explosive cyclogenesis threshold. Minimum central pressure approximately 948 hectopascals near peak intensity. Peak impacts: hurricane-force wind gusts along the New England coast, blizzard conditions, coastal flooding during high tide and significant snow totals from the mid-Atlantic to Maine. That single storm reset many of the operational benchmarks for what bomb cyclones could do along the east coast. The pressure drop was nearly 2.5 times the threshold for bomb classification. The wind impacts reached hurricane force in many locations. The coastal flooding during high tide cycles produced damage that took months to fully repair. Grayson is one of the names that gets whispered when a current storm starts to look like it might match or exceed historical levels. Forecasters reference Grayson the way doctors reference particularly memorable cases. The comparisons are not always exact, but they help frame the range of what a storm can do. Other names get referenced too. The perfect storm of 1991, the Halloween nor'easter that produced what became the popular book and film, the President's Day storm of 1979. Each one is remembered for specific characteristics that distinguish it from the average run of major coastal events. For the current bomb cyclone, the comparisons are still being formed. The peak central pressure is forecast to be lower than Grayson's worst values, but the location and trajectory are similar. The wind field is expected to be smaller in radius, but potentially more intense at the peak. The coastal impacts may be limited compared to Grayson's record-breaking levels, but in some specific zones, they could match. The historical context matters because it provides calibration. Forecasters and emergency managers use historical analogues to help anticipate what a current storm might do. If a storm looks similar to a previous event, the same kinds of impacts are likely. If it looks different, the differences need to be analysed carefully to understand what they mean for the current threat. The Grayson comparison for the current storm is partial. The seasonal timing is different. Grayson was a winter storm. The current event is a late spring system. The specific atmospheric configuration is different. Grayson formed in a much colder air mass with different upper-level features, but the broad track, the rapid intensification rate, and the bomb cyclone classification are all similar enough to make the comparison useful. Other comparisons that have been raised in operational discussions include several mid-Atlantic coastal storms from the past several years that produced significant rain and wind impacts without the snow component that defines. Winter bomb cyclones. Those events caused substantial coastal damage even without the blizzard conditions that get the most attention from public media. The May timing of the current storm is unusual for a major bomb cyclone. Although strong extratropical systems are less frequent in early May than during winter, spring transition patterns can support rapid intensification over the western Atlantic. The recognition that spring bomb cyclones are possible is becoming more widespread, but they remain rarer than their winter counterparts. The atmospheric conditions that favor them are typically present during a narrower window of time, usually associated with strong cold air outbreaks meeting unusually warm spring sea surface temperatures. For the current storm, the conditions have lined up almost perfectly. The cold air outbreak is robust, the Atlantic is warm, the upper level pattern is supportive. The result is a system that is going to be remembered, even if it does not break records. The naming convention for these storms varies. The National Weather Service does not officially name extratropical cyclones in the way the National Hurricane Center names tropical systems, but media organizations and private forecasting companies often assign names to make communication easier. The Weather Channel has its own list. Various universities and meteorological organizations have proposed alternative naming schemes. Whatever name gets attached to the current storm, it will likely be referenced in future events. Forecasters facing similar setups in coming years will look back at this event and use it to anchor their thinking. The data collected from this storm will help refine the models that will forecast the next one. The whispered names of the past inform the work of the present. The current storm is in the process of becoming one of those names. When a major weather event hits, the financial machinery of disaster response begins to move. Most of it is invisible to the general public, but the cost of a single storm can ripple through federal, state, and local budgets for months or years afterward. The Federal Emergency Management Agency operates a disaster relief fund that pays for federal assistance after major disasters. The fund is replenished by congressional appropriations, but its balance can be drawn down rapidly during particularly active periods. When the fund runs low, FEMA goes into a mode called immediate needs funding, which restricts spending to the most urgent active disasters and delays payments for older recovery efforts. The current bomb cyclone is going to trigger federal disaster declarations in multiple states. Each declaration unlocks federal cost sharing for state and local response efforts, federal hazard mitigation funding for projects that reduce future damage. The total federal cost depends on the severity of the impacts, the number of declarations issued, and the duration of the recovery period. For a major bomb cyclone with widespread impacts across multiple states, the total federal cost can run into the billions of dollars. That is on top of the costs incurred by state agencies, local governments, private insurance, and individual property owners. The cumulative burden on the federal disaster response system has been climbing. Major events are happening more frequently. The cost per event is rising due to inflation, increased coastal development, and increasingly damaging storm characteristics. The fund balance is tested regularly. Earlier in 2026, FEMA leadership transition added additional uncertainty to the federal response apparatus. FEMA head resigns. Reporting from earlier this year noted significant changes in agency leadership. For the current storm, the federal response will be coordinated through the Standard Emergency Management Framework. Pre-positioning of resources has been underway since Friday. Coordination calls between federal, state, and local agencies have been happening daily. Disaster declarations are likely to be processed in the days immediately following the worst of the impacts. The state-level financial picture is also significant. State emergency management agencies maintain their own response funds, and those funds get drawn down by major events. States like North Carolina, Virginia, New Jersey, New York, Connecticut, Rhode Island, and Massachusetts are all in the projected impact zone. Each of these states has experienced significant disaster events in recent years, and their available response capacity varies. Local government finances are tested most acutely. Counties and municipalities along the affected coast bear the immediate costs of debris removal, infrastructure repair, and continuing emergency response. Many of these costs are eligible for federal reimbursement, but the reimbursement process can take months or years to complete. In the meantime, local governments have to front the money out of their own budgets. For many small coastal counties, a single major storm can consume the entire annual emergency reserves. Subsequent events can push them into deficit territory. Multiple events in close succession can require emergency state intervention or federal advance assistance. Private insurance covers a large portion of the property damage from major storms, but the scope of coverage varies. Standard homeowners policies typically exclude flood damage, which has to be covered separately through the National Flood Insurance Program or specialty insurers. Wind damage is usually covered, but with deductibles that can be substantial. Beach erosion is typically excluded entirely. The result is a patchwork of coverage that often leaves significant gaps. Property owners discover after major events that their actual insurance recoveries fall short of their actual losses. The gap has to be filled either by personal savings, federal disaster assistance, or simply absorbed as uncompensated loss. The cumulative effect of repeated major events on coastal economies has been studied extensively. Communities that take repeated hits tend to lose population over time as residents move away from continuous risk. Property values can decline despite the desirable location. Local tax bases shrink. The communities that remain face a slow downward spiral. Some places have managed to break the cycle through aggressive investment in resilience. Building codes have been strengthened. Flood barriers have been constructed. Critical infrastructure has been moved to higher ground or hardened. These investments are expensive, but have shown measurable benefits in reducing damage from subsequent events. Other places have not made the investments, often due to lack of resources. Those places remain vulnerable, and each new event makes them more vulnerable still. The current storm is going to write a new line in this long ledger. Federal funds will be allocated, state reserves will be drawn down, local budgets will be stretched, private insurance claims will be processed, property owners will receive whatever recoveries they can. When the spreadsheets are added up in a few months, the storm will have a price tag attached to it. The price tag will join a long list of similar price tags, and the budget pressures that have been building for years will be incrementally worse than they were last week. The financial costs are the lasting echo of any major storm. The wind passes, the rain stops, the water recedes, the bills remain. Every major storm has a final hour before impact, when the decisions stop and the waiting begins. The preparations are finished. The warnings have been issued. The evacuations are complete, or, in the cases where they did not happen, will not happen now. The forecasters who have been working the case for days enter a strange phase. Their job shifts from prediction to verification. They watch the storm do what they predicted it would do, or something different. They update the public messaging in real time. As conditions evolve, they flag any new threats that develop unexpectedly. For the current bomb cyclone, that final hour is approaching for the first communities in the impact zone. Coastal Virginia and the Outer Banks are the leading edge. Wind has already begun to pick up. Rain bands are organizing. The first reports of minor coastal flooding are coming in. The forecasters are watching several specific things in these final hours. The actual pressure trace is 1. Surface buoys offshore, drifting weather sensors, and analysis from satellite microwave instruments combine to give a picture of how rapidly the storm is actually deepening. If the pressure is falling faster than the forecast, additional impact upgrades may be needed. If it is falling slower, the upper end scenarios can be relaxed. The wind field expansion is another. As the storm intensifies, its wind field typically grows outward. Hurricane force gusts that initially cover a small area near the center can spread to cover much larger zones. Forecasters monitor this expansion to identify communities that might suddenly find themselves in the high wind area when they thought they were on the periphery. The track is the third major variable. Even small adjustments in the storm's trajectory can shift the worst impacts from one community to another. A storm tracking 50 miles farther east than forecast brings significantly less impact to coastal cities. A storm tracking 50 miles farther west brings significantly more. The interaction with the upper-level pattern is the fourth. As discussed, the closed low over Canada is acting as the puppet master for the surface storm. If the upper-level pattern shifts unexpectedly, the surface storm can move in unexpected directions or behave in unexpected ways. In these final hours, forecasters often find themselves talking to other forecasters more than to anyone else. Coordination calls between regional offices happen frequently. Conversations between agencies are continuous. The shared expertise of dozens of trained meteorologists is being focused on the immediate threat. The fears that experienced forecasters carry in these moments are not the obvious ones. They are not afraid of the storm itself. They have seen many storms. The storm will do what storms do. They are afraid of the things that could make this storm worse than they predicted, a sudden additional intensification phase that the models did not capture. A track adjustment that puts an unexpected community in the path of the worst impacts. A secondary cyclone that develops faster than the warning system can respond to. A vulnerable population in a specific location that did not receive the warnings or did not act on them. These fears are not paralyzing. The forecasters keep working. The forecasts keep being issued. The warnings keep being updated. But the awareness of how badly things can still go wrong, even after a week of preparation, keeps experienced minds focused. For the public, the final hour is a different experience. The waiting is the hardest part. The wind starts to rise, the rain begins. The first power flickers happen. Cell phone batteries get topped off one more time. Children are gathered close. Pets are brought inside. The kitchen flashlights are tested. The bathroom is identified as the safest interior room. The plywood on the windows is checked one more time. The cars are positioned away from large trees. The gas tanks are full. And then everyone waits, because that is all that is left to do. The bomb cyclone is real. It is offshore. It is deepening. It is approaching the coast. The storm is here. For the next several days, communities along the eastern seaboard are going to find out how well their preparations match the reality of what the storm actually delivers. Some will come through with limited damage. Others will be reshaped by the experience. What is certain is that the storm forming off the US coast is worse than the original predictions suggested. The forecasters caught the upgrade in time to issue appropriate warnings. The communities have responded to those warnings as best they could. The infrastructure has been hardened where possible. The rest is up to the storm and the ocean and the air and the energy that has been building up offshore for the past several days. The forces that drive bomb cyclones are now in full play. The geography of the East Coast is doing what it always does in these situations. The result will be written by Tuesday morning. The forecasters will analyze it. The emergency managers will respond to it. The communities will recover from it. The federal disaster system will fund it. The insurance companies will pay out for it. The news cycle will report on it for a few days before moving on to the next event. But the lessons learned from this storm will inform the next one, and the one after that. The cycle will continue, as it always has, with each event teaching the system a little more about what is possible. The storm is forming off the US coast right now. It is worse than predicted, and the next several hours will determine just how much worse.